Good afternoon, everyone. I hope the video and audio is clear. For online people, I hope the video and audio is clear. Good. So good to see some people here also. So today we'll have around 5 hours of class, total of 5.5 hours. I'll give you half an hour break between the classes. So today I'm planning to finish astrophysics, which will include all the basics of astrophysics and recent inventions and discoveries related to astrophysics. And then we'll be stepping into nuclear science. If the classes are fast enough, if it's picking good pace, I'll give you basic introduction to nuclear technology also. Good. A quick revision of what we dealt in the last class. So last class we were talking about some of the important missions such as GRACE FO. Work agala idu. Hold on. Duplicate put the video play on na probably. Right, okay. யார்ட்டையும் சொல்லுங்க எல்லா கிளாஸ்லயும் இது ப்ராப்ளமா இருக்கு. பவர் பாயிண்ட்க்கு இதுக்கு ஷிஃப்ட் பண்ண முடியாதுல்ல இருந்து பண்ணலாமா? போனா போர்டு மறுபடியும் ரிட்டர்ன் வருதுன்னா ஓகே. ஆனால் பவர் பாயிண்ட் ஸ்லைட் ப்ளே பண்ணிட்டு அதுக்கு வர முடியாது. இப்போ நீங்கள் ஸ்லைட் ஷோ கொடுத்துட்டுனா அதுக்கு வர முடியாது இல்லையா? இப்போ நான் என்ன சொல்கிறேன்னா இது இதுலேயே அட்ஜஸ்ட் பண்ணிட்டு ஒர்க் அவுட் ஆகி this is better. So the last class we were dealing with a mission called as GRACE FO. It's a follow-on mission that is used for mapping the average gravitational field of the Earth. So why do we map average gravitational field of the Earth? We'll be using the data to check how the aquifers are recharging, how water is moving around the world, which includes all the polar ice caps, all the oceans, and also the underground aquifers. And then we were talking about something called as ISAT. ISAT-2, the most recent mission is the second satellite that's called as ISAT-2. ISAT-1 was the first mission by NASA, followed by a follow-on mission that's called as ISAT-2. So basically the primary mission of ISAT-2 is to check the thickness of the ice caps. So basically even if the ice cap is going to vary by a thickness of around 4 millimeters, by a small amount of thickness, so it can easily detect that and it will be tracking the variation in thickness. So also I told it will be tracking the area, the slope and thickness of the ice caps. That's the overall idea of the mission. And followed by that, what was the next topic? We were dealing with Starlink. Yeah, Starlink. It's an internet service based on satellite. So I told you all the satellites will be put in low Earth orbit, not on medium Earth orbit or not on high Earth orbit. So basically, we'll have low altitude satellites which will be placed somewhere around 500 kilometers above the surface of Earth. So and using this, we'll be getting internet connection. So the most important problem associated with Starlink is large amount of space junk and crowding in the low Earth orbit. So which means if we are planning to put some other observatory, or if you're planning to launch more satellites into the orbit. It will be obstructed by the 1200 satellites that will be launched by Starlink. That's the main problem associated with Starlink. And I told you there are some other competitors that are coming into the field. Namely, we have OneWeb, which is partially owned by Indian company called as Bharti Group. So OneWeb is 50% is owned by UK government and 50% is owned by Bharti Group. And other than that, we have Amazon's satellite-based internet service connection that's coming up. That's called as Kuiper. And then we have LeoSat and CanadaSat. These are some of the satellite-based internet connections. And after that, we were starting with the basic principles about the Big Bang theory. So I told you basically Big Bang is, it happened before 13.7 billion years. 13.7 billion years. So what happened between 13.7 billion years? It was everything was compressed in a small ball of matter, which was infinitely small, which was infinitely hot. And all of a sudden it expanded or it exploded. So what happened after the explosion? I told you there were many things that happened before the first 3 minutes. So before first 3 minutes, what happened? Initially, gluons were annihilating to form quarks, and quarks were separating to form gluons. So that was the first process I told you to remember, which is around 10⁻⁶ seconds after the Big Bang. What was happening? Quarks, gluons. This cascading effect was there, and gluons fused to form quarks. And again, quarks formed gluons. Gluons annihilated to form quarks. So this went on and on and on. And when energy was saturated, when there was no more energy for annihilation and separation of particles, we only had quarks that was left over. So quarks are building particles of the modern days. The protons, neutrons, electrons, and everything. So what happened? Based on different combination of sparks, based on different amount and different spin of the quark, we have different elementary particles, which will include hadrons, leptons, mesons, and everything, which will also include neutrons, protons, and electrons. So if you remember the fact which I told, neutrons, protons, and electrons, which one has the highest mass of these three? 1, 2, and 3. Can someone say which one has the highest mass? Of these three elementary particles, which one has the highest mass? Okay, neutrons has the highest mass, because I told you neutrons, they are much heavier. Even though they are neutral, they are much heavier. So basically neutrons, they undergo beta decay and they form protons and electrons. After Big Bang, this is how protons and electrons are formed. Basically neutrons decayed and it produced protons and electrons. I told you the lightest particle in this is electrons. And the fastest particle would be electrons, because lighter the faster. Remember it that way. It's like running a 100-meter sprint. If the particle is going to be lightweight, it's going to run faster. So electrons has much lesser mass, but it can travel at higher speed. For comparison, I told you rest mass of one proton equals to 1,836 electrons. This is given in your NCERT. So basically, imagine having a physical balance. If you place one proton on one side, on the other side you have to place around 1,836 electrons so that you can balance it. So which means electrons has almost negligible mass, much lesser mass. Good. And followed by that, after proton, neutrons, and electrons, everything formed in the 3rd minute, that is exactly around 180 to 200 seconds after the Big Bang, slowly atoms started forming. We call it as nucleosynthesis era. So basically, unstable hydrogen, unstable deuterium. What is deuterium? H11 is hydrogen, which is called as protium. H12 is called as deuterium. So basically, hydrogen nucleus with one neutron, which is unusual. This is all unstable. So unstable atoms started forming, nucleus started forming in the 3rd minute. And after that, slowly matter and radiation started forming and forces started forming. I told you about 4 important forces. What are they? One is gravitational force, that is ruling the entire solar system. So gravitational force, and then we have electrostatic force. That is the positive and positive ripple, or negative and negative ripple. Positive and negative charges attract. So it's guided by a force called as electrostatic force. So first gravitational force, second we are talking about electrostatic force, and 2 other forces are strong nuclear force and the weak nuclear force. So other than this type of attraction, there is one more type of attraction that exists only inside nucleus of an atom. So only inside the nucleus, which means the distance is less than 10⁻⁻15 meter. Both the positive and positive charges will attract. Even if there is negative and negative charges, it will attract. So basically, it is charge independent attractive force. That's called as strong nuclear force. So gravitational force, electrostatic force, strong nuclear force. Then weak nuclear force is the force that is guiding the decay of neutrons into protons and electrons. So we have 4 fundamental forces of nature. So slowly matter, radiation, forces, and everything started forming. And we have passed 3 minutes after the Big Bang, and after around 300,000 years. So in some sites it's given us 300,000 years. In some sites, based on European prediction, it is given as 380,000 years. It depends, it varies. So roughly around 300,000 years, stable nucleus started forming, which means nucleus trapped electrons around them. So electrons started orbiting nucleus. So this thing formed after 380,000 years or 300,000 years. And slowly what happened, then hydrogen and everything started fusing and they started forming heavier elements. So I showed you the periodic table. We started with hydrogen, followed by that we had hydrogen, helium, lithium, beryllium, boron, carbon. It went on and on and on. So this process is guided by nuclear fusion process. So basically when two or more lighter nuclei or two or more lighter elements, if they fuse and they form a heavier element, then it's called as nuclear fusion. For example, in general, the nuclear fusion, 4 hydrogen atoms, they'll fuse to form helium, which will be aided with the emission of 2 positrons and 2 neutrinos. So this is a process that's called as nuclear fusion. So basically, hydrogen will fuse to form helium, helium will fuse to form lithium, and it goes on and on and on. That's how it was formed. So it went on until iron. So till iron, everything was formed inside the star because of nuclear fusion. All the elements up to iron. So iron has 26 atomic number and 56 mass number, which means 26 protons and electrons, and rest of the 30 are neutrons. So this iron, till iron, it was formed inside the stars. Good. So after that, what happened was it was the stars did not have enough energy to fuse it, and followed by that, star underwent explosion called a supernova explosion. So because of supernova explosion, large amount of energy was created, which further fused elements like iron, and then it formed all the heavier elements like up to uranium and everything. It were formed not inside the star but outside the star. Very important fact to remember. So all the stars, they can form elements till iron inside them. So all the elements after iron in the periodic table, it's not formed inside the star by nuclear fusion. It's formed outside the star in the galaxy because of supernova explosion. So the energy created, the recoiling effect and the kinetic energy created because of supernova explosion, it will cause further fusion of elements after iron. That's one thing to remember. And then we were talking about life cycle of star, right? So life cycle of star is very much important. We were classifying stars into 2 types, low mass star and supermassive stars. So this is the lesson plan for today. Before we start, I think we have completed till this black hole. So rest of the things we have to deal today. This is the plan for today. So it might look large. We'll try to complete. Good. So Big Bang is over. I have to talk about Hubble's law. So what is Hubble's law? Basically, it says the universe is expanding. Is it expanding at a faster rate or a slower rate compared to the old data, or compared to the older rate? Is it faster or is it slower? It's actually faster. It's accelerating. The expansion of universe, it is accelerating. In recent times, it is accelerating. Even the people online try to participate, try to post your answers. I'm watching your messages. Good. So based on Hubble's law, what he says is when the distance between the 2 galaxies increases, the recessional velocity also increases, which means the rate of drifting away, it keeps on increasing. Good. So what we think is there is something that is filling the spaces between the galaxies. We call them as dark energy and dark matter. I told you all we know is only 4%. So all the matter and all the radiation which we come across, all the galaxies, stars, everything in the universe, we know only 4% of it, and rest of the 96% is unknown because we cannot feel. They do not interact with electromagnetic radiation. So can someone remember the electromagnetic radiation spectrum? Even people online, you can post it, type it as a single message. We'll start with the radiation with highest wavelength. The radiation with highest wavelength, that is radio waves. You have to start with radio waves. Can someone tell the electromagnetic spectrum? Because today we'll be talking about electromagnetic spectrum a lot. We're starting with radio waves. Followed by radio waves, what is next? Microwaves. Yeah, we have microwaves. Followed by that, we have infrared rays that is emitted by basically thermal radiation. Followed by that, we have visible light. So visible light is all the light that we see. All the Webjer color, it's classified as visible light. And then, yeah, we have gamma, X-ray, UV, visible, IR, micro-ray. Good. So then we have ultraviolet rays. Followed by that, we have the ionizing radiation, that is X-rays, and followed by gamma rays. So all these are a form of electromagnetic spectrum. So and we could see only this much. That is only visible light is visible to us. We are evolved in such a way that we could sense only visible light. Rest of the things we predict them based on the interaction with other objects. That's how it works. So all these forms only 4% of the universe. So rest of the things we don't know, because dark energy and dark matter, they do not interact with any of these electromagnetic waves. So we predict it only by the presence of gravitational waves, nothing else. So only it interacts with the gravity, or because of the interaction of the nearby objects, we say there is something called as dark energy and dark matter. We don't know what is present in the dark energy. We don't know what is present in the dark matter. Is it made of elementary particles? Is it made of mesons, gluons? We have no idea. Just like the center of the black hole, we have no idea about it. Good. Then talking about the life cycle of star, I think we have a much easier way to revise this. We have completed these. Yeah. So we're talking about two different types of star. First thing was protostar. So protostar, what is protostar? There's something called as nebula, basically the star space. So what happens in the star space? Basically, particles come together, especially hydrogen atoms comes together. It starts spinning. So because of the spinning, what will happen is there will be a large amount of kinetic energy, and because of large amount of kinetic energy, it emits a small amount of radiation, and then it compresses. And because of the compression, it becomes relatively more stable. So that's what you call it as main protostar. So protostar is basically by nuclear fusion, and then even more it compresses, it becomes even more stable. That is called as main sequence star. So main sequence star is the most stable star. Proto is unstable. So I told you to remember Proto-Shiva in Indus Valley civilization. So basically proto is something that has not formed, that is unclear. So a protostar is the beginning stage of the star, and then we have the main sequence star, where hydrogen starts fusing into helium. So basically 4 hydrogen starts fusing into helium. That's the second step. And then again, as it fuses, what will happen is somewhere the hydrogen supply will run out. So which means the star will only have helium. It will not have hydrogen. So what will happen? It will stop fusing. I told you there should be a delicate balance. That's called as hydrostatic equilibrium. I told you. So basically there should be a balance between the radiation from inner side of a planet or a star and the gravity. So there should be a balance between gravity that is pushing the star inside and the radiation that's coming in from the star in the outward direction. So when the balance is lost, what will happen? If radiation is exceeding, the star will explode. If the gravity is exceeding, the star will implode. So what is implosion? Implosion is basically like a compression, where an explosion is something like a blasting off. Good. So in this case, the radiation stops. What will happen when the radiation stops? The gravity will take over. Because of the gravitational influence, the star will collapse under its own gravity. It's called as implosion. So because of implosion, it will attain something called as red giant phase. So red giant phase, it is relatively cooler. I told you, in terms of flame, if you take white flame, blue flame, and red flame, red is relatively cooler. White is much hotter, and blue is comparatively hotter. So I told you the example of the gas stove. If there is any dust inside the gas stove, what will happen? It will burn, the flame will be somewhere orangish to reddish. So that's because there's improper combustion, the temperature is relatively low. If you look at the center of the flame, it will be blue, and even more the most center part in the candle flame, it will be white. So whiter the flame, hotter it is. Blue means complete combustion, but lesser temperature. Red means even lesser combustion, and it has lesser temperature. So of all these, red giant phase has much lesser temperature. So that's why it appears red, but it is cooler. So what will happen? Again, the star will compress. It attains something called as red giant phase. So from this, we are dividing it into 2 types based on mass of the star. If the star has less than 10 times the solar mass. So I told you it m naught, which is the mass of the sun. If it is less than 10 times the solar mass, we classify it as low mass star. So what will happen? Low mass star, helium will fuse to form carbon, and then again it will collapse once again because there is no more energy left over, and it will form something called as planetary nebula. So basically the implosion is called as planetary nebula. So followed by planetary nebula, whatever is left over is called as, the remnants of the implosion is called as white dwarf. So white dwarf is white in color, and then it begins to cool down into black dwarf. So this is the basic which I have given. The main reason for revising this is there are some other subdivisions based on this. We'll be dealing with it today. Good. And then coming to the high mass star. So if it's a massive star, what will happen? Hydrogen will fuse, helium will fuse into carbon, carbon will fuse into iron. It goes on, and it stops at iron. So once it attains the iron stage, it cannot undergo further fusion. So the star will once again implode. So what will happen when the star implodes? All iron will be crushed together. What happens when the iron is crushed together? The nucleus come nearby, and once the nucleus is crowded in the middle, the positive charge will repel each other. So, and because of that, after the implosion, there will be explosion. So the star will explode. Iron will be seeded into the the external space. That's called as supernova explosion. This is the first place we are using the term explosion. Remember, all these time we were talking only about implosion. So basically, yeah, star collapsing under its own gravity. This is the first time star is expelling something outside from the inner side, from the core area. That's called a supernova explosion. So after supernova explosion, based on the remnants of the supernova explosion, we are classifying it into 2 types. One is neutron star, the other one is a black hole. So if the remnant is less than 1.4 times the solar mass, up to 3 times the solar mass, there is 3 into the mass of the sun, it becomes a neutron star. So generally neutron star appears as binary. You can write it down. Mostly neutron stars, they won't appear as a single one, they appear as binary because they'll be orbiting on a common axis. There will be two neutron stars together. Sometimes it's called as a neutron star binary, NSB. Good. And then coming to black hole, if the mass is more than 3 times the mass of sun, it becomes what is called as a black hole. Good. So we were talking about black hole. 3 important components of black hole. The first thing was event horizon. So what is event horizon? The point of no return. Once the object crosses the event horizon, to escape from the influence, it has to travel at a rate of more than the speed of light, which is almost impossible. Till now, the fastest thing we know is the speed of light. Good. And then singularity, the extreme core part of the black hole is called a singularity. So what is singularity? We don't know. All we know is there is no proton, electron, neutron, or anything. Everything is compressed in basically the spaghettification process, where everything is crushed and squished into a single form. That's called a singularity. There was a UPSC question also. I displayed the sample question. So there was a UPSC question about singularity. We don't know what is inside singularity. In the option it was given, it helped us to understand what is mean by singularity. The answer is no. Till now, till date, till 2021, we don't know what is mean by singularity. So the research is still going on. We don't know what is mean by singularity. And then talking about Schwarzschild radius. So the distance between the singularity and the event horizon, that's called as Schwarzschild radius. The 3 important components of black hole. I think you wouldn't have written this single definition. You can write down about Hubble's law if you want. I updated it. Yeah. Recessional velocity is Hubble's constant into distance. Good. Coming to the next one. The recent discoveries by the physicist from Indian Institute of Astrophysics. So we have lithium-rich stars. So that's the most recent discovery. We have completed these. First thing is lithium-rich stars. So why it is peculiar is, I told you hydrogen fuses to form helium and then helium fuses to form lithium. So if it is forming till carbon, the stars are supposed to have lesser lithium, right? Because hydrogen will become helium. So once it runs out, the star will compress. Then helium will form lithium. Once it runs out, it will compress. So if you take it this way, the stars are supposed to have lesser lithium. So where do we use lithium predominantly? We use it in battery technologies. We have lithium polymer, lithium ion batteries. So lithium, it's light element. And most importantly, most of the lithium which we use, it's from stars explosion. So stars explosion, it has seeded lithium to the universe. The main peculiarity is, how do stars have higher lithium? That was one mystery. So the lithium-rich stars, they were discovered somewhere close to 20 years before. So it's been a 2-decade mystery, how lithium is present in the stars. How stars are rich in lithium, that was one problem. So the one firmly believed theory was planet engulfment theory. So because imagine a star is nearby the planet, and then the planet jumps inside the star, and then it consumes. What will happen? All the lithium in the planet will go to the star. So in this way, the star may have enriched uranium. This was one theory that was propounded, but that was clearly ruled out. Right now, what they have discovered is, after red giant phase. So I told you the sequence of the star. After the red giant phase, there is one more phase called as red clump stage. Good. So recently it has been discovered by IAA scientists. So in this red clump stage, especially in the low mass stars, we are talking about low mass. We are not talking about supermassive stars. Good. So in low mass stars, what happens is there is a process called as helium flash, a new term that was discovered by the scientists. Because of the helium flash, what will happen is helium will fuse and form lithium. So that's why lithium is present in the stars. You can write it down. First, why it is peculiar? Because all the lithium around 1/4 of the lithium formed during the Big Bang, it is consumed. So even sun has much lesser lithium compared to the Earth. All the lithium is being consumed by the fusion. This is important. The abundance of lithium, it's just 1/4 compared to the Big Bang value. So the abundance of lithium, it's reducing. It's supposed to reduce. But then note on this alone, only 1/4 times compared to the Big Bang value. So stars generally consume lithium. If you see here, to form everything, it has to form lithium, which is the third element from the periodic table. So even if it's going to form till iron, definitely the star should consume lithium. But then it's because of red clump stage and because of something called as helium flash. Sometimes there'll be easy questions like this. What is meant by a helium flash, which was in news recently? What is meant by grease lightning that was there in news recently? It was a 3-year-old question. So remember helium flash, it creates more lithium inside the stars. Yeah. So this was recently discovered. And second thing, we have to talk about type 1a supernova. I'll tell you why it is important. So there was one more theory given how lithium is found on the Earth. So how the abundance of lithium increase on the Earth. So that's based on type 1a supernova explosion. So take a look at this. So when we see the low mass stars, I told you protostar to red giant to planetary nebula, and then we have white dwarf. So these white dwarfs, they have much lesser mass. Am I right? Because if you see neutron star, it has mass somewhere around 1.4 times the solar mass up to 3 times the solar mass. I told you. If you take the black hole, it has mass greater than 3 times the solar mass, which means this is for massive star. Now we are talking about white dwarf, which is from a low mass star, which means its mass should be much lesser than the solar mass. So what will happen is sometimes white dwarf may not be a singular system. Sometimes it becomes a binary system, which means if there is some star nearby, what it will do is it will take elements or it will engulf matter from that star. So what will happen is what happens when you consume more energy, you keep on growing. So white dwarf keeps on growing. And once it attains the Chandrasekhar limit, that is called as 1.4 times the solar mass. You remember we were talking about it here. Good. So once white dwarf grows into the Chandrasekhar limit, it cannot consume any more matter and it will explode. So because of this explosion, more lithium will be seeded into the universe. This is one more theory. Two theories totally. Good. So lithium abundance is especially from low mass stars. This is important. We are not talking about, we never spoke about massive stars in this entire topic. Good. Next one. The keyword is low mass giant stars, not supermassive stars. And the next one, type 1a supernova. Where does it happen? Does it happen in neutron star? Does it happen in white dwarf? Or does it happen in black hole? It happens in white dwarf. Good. So white dwarf, a small animation for you. So this is what happens. A star is nearby. What it will do is it will consume. So basically the entire thing is consumed. Once it crosses the Chandrasekhar limit, that is 1.4 times the solar mass, it will explode. So this is what happens to a white dwarf when it consumes more mass. So and because of this, during this explosion, a large amount of lithium will be seeded into the star space, into the interstellar space. So this is the key point, not to be missed. Clear? So the detonation of stars, sometimes it's called as thermonuclear supernova. So thermonuclear. Understand this is related to nuclear fusion reaction. So whenever you see the term thermonuclear anywhere, remember it's related only to nuclear fission. It's not related to nuclear, sorry, it's related only to nuclear fusion, not related to nuclear fission. All the fusion reactions are called as thermonuclear reaction. The main reason is all these happens in extremely high temperature and extremely high pressure. So when a reaction requires high temperature and high pressure to happen, you call it as a thermonuclear reaction. So it's nuclear fusion that requires high temperature and high pressure. That's why it's called as thermonuclear supernova. Good. So most of the lithium, it's because of the classical supernova. Type 1a is called as classical supernova. Somewhere in newspapers, they have given it as IA. It's not IA, it's type 1a. Even Indian Express, I think. I don't know the newspaper's name. It was given as IA. It's not IA, it's type 1a. So if you read the type 1a supernova, people online, if you have any doubt, please drop your messages then and there. Don't wait for individual doubt clearing session. It's also called as classical supernova, main reason for lithium presence. Lithium is repeatedly there in the IAEA news bulletin for the past 2 years. So learn a little about lithium. So mainly used in lithium ion, lithium polymer batteries, which are new type of batteries. Thermonuclear supernova. So Ashwin is saying, okay. See, when we are talking about low mass stars, I told you there is a system called as white dwarf. And once white dwarf cools down, it becomes black dwarf. This was the life cycle of a star. So right now, we do not have any black dwarf all throughout the universe. In the entire universe, there are no black dwarf. So the main reason is I told you the oldest known white dwarf, it has run only out of 0.2% of its fuel, which means the fuel is not going to run out in any closer time. It's going to take numerous amount of time. So the oldest stars are, white dwarf stars. So we do not have black dwarfs. So these white dwarfs, they're supposed to cool down. That is the actual sequence. But one more thing could happen. If there is one more star nearby, much closer, it will form a binary system. It will engulf all the matter present in the star. So if it's going to, white dwarf is going to dominate, what it will do is it will engulf all the matter present inside the other star. So what will happen once it starts consuming? Imagine white dwarf is eating up some other star. So it will slowly grow. So when it grows in mass, maximum limit is 1.4 times the solar mass, which is called as Chandrasekhar limit, CSL. So once the Chandrasekhar limit exceeds, the white dwarf cannot sustain the reaction and then it will explode. That explosion is called as thermonuclear detonation. This is not supernova. This is thermonuclear detonation, we call it as. That's why we call it as type 1A supernova. This is a different type of supernova. Good. Clear, Ashwin? Yes. So sun is a proton star. Sun is a yellow dwarf star. And one important thing is, lesser the mass of star, more time it's going to survive. Good. The lifetime of the star, it's inversely proportional to mass, which means if the star is going to be massive, it's going to be destroyed sooner. Wherein the sun is a yellow dwarf star, it's relatively stable. Constantly, it's in the hydrogen helium phase. It has not crossed that phase alone. So it's in the very first phase. We have a large amount of hydrogen fusing to form helium. If you remember the first class, I gave you different regions of the sun. It started at core, then we had radiative zone, then we had convective zone. What does it mean by convection? Imagine boiling a water. So what the hotter water inside the, like in the bottom of the vessel, it will come up. So and then the cooler particle, it will go down. So this reaction is called as convection. Imagine water comes like this and then it goes like this. So there is a cycle that is set in. So sun has a similar type of cycle. That's why we call it as convective zone. Whatever it's forming, it's pushing outside. So which means sun is relatively stable. It is not going to some other phase. It's more stable. Clear? Yes, thermonuclear supernova is also called as type 1A. Type 1A is the classical supernova. The main reason why we have lithium and everything on the Earth now. Archana, clear? And Akash, is it clear? Website to read about lithium? No. I didn't tell about any website. I told you Indian Institute of Astrophysics, IIA, the research organization. They have many news bulletins related to lithium. One such thing is reading about M dwarf stars and reading about the helium flash. Once the white dwarf explodes, it forms thermonuclear supernova. Yes, Sri Lakshmi, correct. When the white dwarf explodes, it forms thermonuclear supernova. Yes, Shivapriya, right now we do not have any black dwarf throughout the universe. The oldest known stars are white dwarfs. No black dwarfs in the universe, no black dwarfs in any nearby time. Coming to the next one, Lumen 16A. So this is important because which is the closest star to the solar system? Any idea? Can someone tell me? Which is the closest star to the solar system? We have a star that was there in news for the past 2 or 3 years repeatedly. It's called as Alpha Centauri system, ALPHA, Alpha. Centauri star system. So basically there are 3 stars in this. There is Alpha Centauri A, B, and Proxima Centauri. So remember, Alpha Centauri is the closest star to the solar system. And next to this, we have Barnard's star. First is Alpha Centauri system. I told you this has 3 stars. And then we have Barnard's star. And the third one is Lumen 16A. So remember, Lumen 16A is the closest brown dwarf. Don't remember it as the closest star system. This is the closest brown dwarf star system. So this is the first time in the class we are talking about something called as brown dwarf. We have been talking about yellow dwarf, red dwarf, white dwarf, black dwarf, and everything. This is the first time we are talking about brown dwarf. Remember, Lumen 16A is a brown dwarf, and brown dwarf is also called as failed stars. So that's because they are not large enough to be stars. They are not small enough to be planets. They are the intermediate between the planets and the stars. And also they emit much lesser radiation. So basically because of fusion of helium and lithium. So generally because of fusion of helium and lithium, they emit a faint radiation. So that's why they are called as brown dwarf, also called as failed stars. Lumen 16A. and Lumen 16b. Both of them form a star system, and in that Lumen 16a was there in the news in the last 2 years. It's a binary system, Lumen 16a and Lumen 16b, binary brown dwarf. Third closest system to the sun. I told you it's the third closest system to the solar system. Write it as closest to the sun. We'll consider it from center of the solar system. They're casting a dim light. Good. So the special thing about the star is recently they have discovered clouds on the star. So basically band of clouds. Band of clouds have been discovered on the star. What is the definition to be called as star? It depends on temperature and the pressure it maintains. It should not have a solid crest. It should have multiple layers of gaseous things. And second thing, it should not be orbiting another star. You know, stars generally they are found inside the galaxy. And second thing, they do not orbit along with the planets. But there is an exception to this called as binary star system. We'll talk about it. Most of the stars, they remain as an individual unit. They may have planets around them. So if there's a star and if there are rocky things that are orbiting around them, we call them as planets. There are multiple criteria. Coming to the next one. So brown dwarfs are called as failed stars. Clear? The most recent discoveries, they've discovered band of clouds. So they employed something called as polarimetry technique. So does white dwarf have elements up to lithium only? They have elements up to carbon. So I told you when it undergoes planetary nebula, it forms up to carbon. So after carbon, it cannot fuse and it explodes, which means it will have all the elements starting from the hydrogen, helium, lithium, beryllium, boron, carbon. So all the 7 or 6 elements in the first 6 elements of the periodic table. It will be present in different composition. It's not a standard composition. It differs based on the star. First 6 elements of the periodic table: hydrogen, helium, lithium, beryllium, boron, and carbon. Don't think it has only 6 elements. It will have isotopes of these elements also. We have C612, C614. For hydrogen, we have 3 isotopes. So all these isotopes and the pure atoms will be present inside. The main reason we are employing polarimetry technique. See, first we'll tell you what is meant by polarization. It's very much important. You can learn the statics part in NCERT. Good. So generally, if you take any electromagnetic wave, it will oscillate this way. So I told you it's electromagnetic wave, which means it has both electric component and magnetic components. So electric component will be oscillating in one direction, and magnetic component will be oscillating in other direction. Good. So what we do is we filter out one of these aspects, and then we get a plain polarized light. The best example is you have polarized glasses. So why do we wear sunglasses when you go out on a sunny day? If you cannot look at the sun directly because it's shiny. But if you wear a polarized glass and then you look at the sun, it will appear just like a dot. So what will happen is, see, light is called as the source. We draw something like this. So even in school time drawings, we'll be drawing like this. That's because from a single point, so light will be traveling in different phases. So imagine a single point of light starting from sun to everything. It will have multiple phases. Good. So if you are going to apply a polarized filter, what will happen is only one phase will come out. So it depends on the type of polarizer you have. So either it will filter out this component, or it will filter out only this horizontal component. Any one component of the light or any other electromagnetic wave, it will be emerging out of the polarized filter. So by using this technique, we are basically trimming out other unwanted radiation, and then we are checking what is present on the lumen. So basically the image that they gave for lumen 16A, basically a simulated image based on the polarized light which the scientists have received. So to make the polarization concept better, take a look at this. Audio play aguma.
Now, Brady, this is the bit that really is going to do your head in.
இங்க கேட்கலையே.
Now, Brady, this is the bit that really is going to do your head in. Which I'm going to enjoy. I'm going to show you how light can be polarized by sheets of Polaroid.
சரி கூப்பிடுங்க, அது ஒன்று ப்ளே பண்ணுறேன். So try to read the subtitles. So just for this first video, we'll fix it in the break.
This is a sheet of Polaroid. It's polyvinyl alcohol with iodine thrown in it. So in here, I'm not sure which way round it is, there are long molecules which are stretched out and they conduct along this direction, but they don't conduct that way. So that's what your Polaroid sunglasses are made of, stuff like this, which is built into it. So it reduces the glare, for example, off the road when you're driving along. So I put a sheet of Polaroid on top of this overhead projector, which produces light, and I put another sheet on top, polarized the same way, and they absorb a bit of light for each direction. But if I turn this top one round so that it is actually perpendicular to that original direction, you can see that you can kill off most of the light. So there's some turning backwards, and that's gone all the way around, and now I'm going back again, and you can see that it disappears. This is an offcut, a bit chopped off from the bottom of this to make it a square. And I can put it on top of these two. Let me square them up. And you can't see it at all. I can put it underneath these two, and you still can't see it. But if I now slide it in between, you can see I'm rolling this up in the bottom corner and sliding it in between, you see you can see it. If I turn it around this way, it disappears. If I turn it round to 45 degrees, you can see something quite strong, and then turn it round a bit more, and it disappears. It's magic. Now you see it, now you don't. Now you see it, now you don't.
Amazing. What's going on?
Well, I find this absolutely fascinating. I couldn't believe this was going to work first, but I'll show you another set of equipment over here, which is some microwaves. This is a microwave generator, and it will generate waves which are polarized in one particular direction. And here is a receiver which will receive them. This wave has a wavelength which is 3 centimeters. Now, 3 centimeters is about yay long, whereas the light wave is 60,000 times smaller. So if I set up traveling waves, waves coming out of here and ending up over here and not being reflected, then it'll be a bit simpler. So I'll detect this by turning this on and getting a very nice big signal. Now I pick up a sheet of Polaroid. This is my sheet of Polaroid. It's just long conducting wires, the same as were in those sheets of Polaroid, but you couldn't see them there. So now I put it in this way round, and you see that you don't get any signal, and I turn it around, and I get a huge signal on the meter at the back. So there it is, nothing gets through, and I turn it around slowly, and you suddenly see the signal appear, and when it's perpendicular, I hit a really big signal on the screen over there. What's happening here is that this is sending out waves which are oscillating with an electric field that goes up and down in this direction. And as the electric field hits this conducting wire, it induces a current in here, and because of the resistance of the wire, this causes the electromagnetic wave to be absorbed and heat to occur in the wire. So it gets totally absorbed by the wire. If I turn it around this way, well, now the electric field causes a little bit of current to go across there, but then it hits the other side of the wire and it doesn't dissipate any energy, it just gets stored there as a capacitance. So this does not absorb nearly as much energy, and so I get quite a large signal. And then I turn it around there and I get virtually nothing. Now,
all right, so that's a basic principle. So now I'll just ask you a question. Question number one, all the electromagnetic waves can be polarized, true or false? That's a true or false based question. So almost all the electromagnetic waves can be polarized. Questions from people online? Electromagnetic waves, yes. So all the electromagnetic waves, they undergo reflection, refraction, interference, diffraction, and polarization. So it's a common property given in your NCERT for all the entire electromagnetic waves. I told you it starts at radio, micro, infrared, visible, UV, X-ray, gamma, every rays. They undergo all these phenomena, so which is common to light. First is reflection, it bounces off. Then refraction, it bends. Interference, basically, adding of waves. And then diffraction and polarization. I told you what is meant by polarization. So all these phenomenon, they are common to almost all the electromagnetic waves. So if you happen to read the NCERT, please go through it again. Good. So understanding the cloud system is important. This is enough. We'll go to the next one. Don't write it down. Next is Event Horizon Space Telescope. This was in the news in 2019 for one main thing. Can someone say what is EHT, Event Horizon Space Telescope? The first thing, it's not a program by NASA. It's not a program wholly run by USA. It's basically a network of 8 radio telescopes that are in different continents. Going to the next phase, it was in the news in 2019 because they released the photograph of the first black hole. The first black hole photograph. It was captured by Event Horizon Space Telescope. It's a network of terrestrial telescopes found in different continents. Most importantly, they operate like a single instrument. Don't write it. We'll be sending it to your Telegram channel. If you see, there are different telescopes in 4 different continents, including Antarctica. There is one in Antarctica, there is one in South America, few in North America, one in Hawaii Island, and one in Europe. So all these telescopes, they capture, microwave, the entire electromagnetic waves coming from different parts, and they coordinate into a single image. So this was the image of the first black hole that was ever discovered. And most important thing about this is, we had 2 questions about black hole in UPSC in the last 5 years. Most important thing is, this part is the black hole. Good. So we cannot see the black hole because, as I told you, light will not escape out from the black hole. So what we observe is, if this phenomenon is called as accretion. So basically, it is taking light from the outer side and then emitting it. This process is called as accretion. So only what we observe is basically shadow of the black hole. We cannot capture the black hole itself. So understand, it's based on how it interacts with the nearby object. So first black hole. It is from a galaxy called as M87. This is important. Messier 87 is one of the largest galaxies which we know. It's located around 50 million light years away. This is one of the first black holes ever captured by the scientist. Please note, India is not a part of EHT program. India does not have any telescopes related to Event Horizon Event Horizon Telescope. Europe, North America, South America, and Antarctica. There is no EHT telescope in Asia. Now we ask a common question. Is there a black hole in Milky Way? The question is there a black hole in the Milky Way? Milky Way is the galaxy in which we live, and the nearest galaxy is Andromeda Galaxy, we know. So is there a Messier Galaxy is one of the galaxies which is situated somewhere close to 50 million light years away. So we have to travel 50 million light years away. Is there a black hole in Milky Way? Definitely yes. So understand, did I tell you two types of black holes? So one is called a stellar black hole, the other one is called as supermassive black holes. So supermassive black holes are extremely high mass and they're generally found at center of the galaxy. Most of the massive, supermassive black holes, they're found at center of the galaxy. And yes, we have a black hole at center of the galaxy. That is Milky Way galaxy. It's called as Sagittarius A. Sagittarius A star. So we have one galaxy at center of the Milky Way. Hold on, I'll write it properly. Sagittarius A is not to be confused with one of the arms of Milky Way that's also called a Sagittarius. So this Sagittarius A star, it's located at center of the Milky Way. So now my question is, we have a black hole which is much closer to the Earth, that is inside the Milky Way. So then why do we take picture of something that is present somewhere around 50 million light years away? So we have a black hole just closer. Then why is that we are capturing from a 50 million light years distance? And the first thing is I was telling about a phenomenon called as accretion. Do you remember? Basically engulfing matters from the nearby object. So the Sagittarius A, it is relatively calm and it does not excrete materials from nearby. So since it's a calm black hole, we cannot detect any radiation around it. So this should actually take matter from the nearby objects and then throw it away. So this thing is not happening in Sagittarius A. It's relatively calm. So for this reason, the most photogenic one is the one in Messier 87, which is excreting a lot of material. So for this reason, we are concentrating there. And don't write anything here. Just read it once. Single telescope, it cannot reach Messier 87 galaxy. So all the 8 telescopes, they are working together, collecting radio waves. And the multiple signals, they are basically stacked together, and then we get a single data like this. Single image captured by multiple telescopes and then stacked together, and then we have a single image. This is important. Excretion disk, thanks. Shivapriya is asking for repeat the types of black holes. Okay. See, first thing we have based on mass, there are multiple classifications. I'm giving you only the major classification. First is stellar mass. Second is supermassive monsters. So the main reason why we call them as supermassive monsters is their mass will be greater than 100,000 times the solar mass. So imagine 100,000 suns, the mass of 100,000 suns. So those black holes will be supermassive. So supermassive monsters. There are a few other classifications. Learn these alone. This is fine. Yeah, I'll show that. Good. Next one. You're saying you didn't write this. No need of writing it. You read it once. Archana, read it once. Don't write it down. Because I'll be sending short notes to you people. Write only running notes. We have more portions to finish. Write only the keywords. Excretion disk, hyphen, hard disk of material around the black hole. That is enough. Don't write the entire slide. The purpose of this slide is to give a reading and then write only the key words. Yes. So accretion disk, the encircling material are called as accretion disk. Good. And the next one. Also understand, we'll be getting a magnified picture of the black hole. We'll not be getting the actual picture of the black hole. The main reason is the process is called as gravitational lensing. So basically, any massive object, it will bend the light and it will show a magnified image. So why it shows a magnified image means, see, take a look at this. I told you black holes have extremely, no, stellar black holes are generally not present at the center. We generally have supermassive black holes. So generally black holes have high amount of mass, which means even light cannot escape out. What will happen whenever light comes in? It will be absorbed by the black hole. So up to 2.6 times the Schwarzschild radius, any light, it cannot escape. So any light that is coming at a distance more than 2.6 times the Schwarzschild radius, everything will be pulled inside. Everything will be pulled inside the event horizon, basically the point of no escape. Imagine somewhere the light gets a point to escape out. Ignore the audio. So more than 2.6 times the Schwarzschild radius. When the light is approaching, it can actually encircle the black hole once and then it will escape. So what we see is these lights. We don't see any of these lights. We see the light that is coming from the topmost layer, more than 2.6 times the Schwarzschild radius. For this reason, the image of black hole is always magnified. Important point. The image of black hole which we receive is always magnified because of gravitational lensing. So the phenomenon is called as gravitational lensing. Don't write the first point, write the second point. So large objects will magnify the light. அடுத்து ஒரு வீடியோ இருக்கும். Done. The next one.
How is gravity like nature's magnifying glass?
Duplicator.
To find out what the universe was like in the beginning, we need to study the most distant galaxies, whose light has been traveling to us. The gravity of massive objects can be so intense that it can warp the fabric of space-time. Light, which normally travels in a straight line through space, can show us where this distortion occurs. A very massive object will warp space and bend the path of the light. In a sense, warped space acts like a magnifying glass. A magnifying glass collects and bends light, making a light bulb, for example, appear bigger and brighter. Warped space can do the same thing to light from a galaxy. So what acts like the biggest magnifying glass in space? Galaxy clusters are the most massive things in the universe with the most gravity. When light from a very distant galaxy passes through a cluster, it is amplified and distorted, with the cluster acting like an imperfect magnifying glass. Light that would have gone in other directions gets bent toward our telescope. that lets us see the very distant galaxy in more detail. This effect is called gravitational lensing. Without this natural boost from gravity, it would be impossible for our telescopes to see far away enough in space and time to study galaxies in the early universe. The Hubble Space Telescope has made use of gravitational lensing to see many distant galaxies. And the larger James Webb Space Telescope will be able to find galaxies even fainter and farther than we've ever seen. With Webb, we will look for the very first galaxies to form and really learn about the early universe.
So whenever you come across news related to James Webb Space Telescope, please take a note of it, because NASA is planning to launch it by 2021, mid of 2021. It's already in a 3 years delay. So pay more attention to it. So the next one, I'm going to talk about Hawking radiation. So the first question, so black holes can die. So there's a possibility that a black hole dies out. Is it true? Black holes have lifetime, so there's a possibility that black hole can evaporate or die. Make a random guess, take a random stance, true or false? Yes, true. So by a process called as Hawking radiation, which was propounded by Mr. Stephen Hawking, the late Mr. Stephen Hawking, what he told was, at the border, at the event horizon, what will happen is there will be a breaking up of particles forming two different particles. So when two different particles form, there is a possibility that one particle escapes inside the event horizon, and there is a possibility that one minute particle, it can escape outside the black hole. So if it continues for a prolonged time, there is a possibility that the black hole will actually evaporate and it will disappear. So that is one theory propounded. So remember, Hawking radiation, it's due to repeated existence and annihilation of particles near the event horizon. This happens at event horizon. So because of quantum vacuum fluctuations, pair of particles will be formed. Something will enter, something will escape out of the black hole. And if it continues for a prolonged time, there's a possibility that a black hole evaporates. The most recent update is it's not possible in near time, because let's say these pair of particles escape for somewhere around 4 months. I'm saying 4 months. The amount of particles that will evaporate in 4 months, it will be equal to 1 photon. The mass of 1 photon. So imagine the mass of a black hole and imagine the mass of a photon, which means it's infinitesimally small. So this escape, it's least possible that it will cause evaporation of black hole, but still it's a theory. Understand? Steady conversion of quantum fluctuations, pair of particles are formed, one particle may escape, and if it continues for a prolonged time, there's a possibility that black hole evaporates. That's all. All right, only the keywords. Done. We have some more close to 3 or 4 more topics to complete astrophysics, which means all related to stars and everything. So I understand it will be kind of dry, because this might fantasize few people who are interested in astrophysics. For few people, it may sound very dry, but understand we have more number of questions related to astrophysics in recent times. Good. So next we have to talk about active galaxy. I think we'll take a break for 10 minutes, refresh and come back, please. We'll complete in another 40 minutes, the astrophysics. Good. Till then, online people, if you have any doubts, please drop your messages here. I'll be available to reply. Yeah, can we start? So I think I answered one of the questions online asking about Hawking radiation. Archana, your doubt is clear. And the next one, Shivapriya, are you online? I've been asking you. So she was asking how polarization works. Are you online? I couldn't see here. Yes. So I'll just share the screen. I couldn't find a better source. So this is how polarization works. I think you won't be able to see. So basically what happens, multiple wave sources, it will be filtered and you get only one single wave source. So rest of the points, it will be filtered out. I hope you could see this. And yes, the next question was from Sri Lakshmi asking what is meant by band-like clouds and how they are formed. Take a look at this. This is how the band-like clouds were formed in Lumen 16A. So basically any light emerging from exoplanet after reflection, it will be polarized. So I told you what is meant by polarization. I told you how the band of clouds looks like in Lumen 16A. You could see it on the screen, people online. So basically it appears like a band, horizontal bands, that because it's appearing like that because of the clouds, and almost all the light source from the exoplanets, it will be polarized. So it's a phenomenon. Is it clear? For Shivapriya, and what are the waves that can experience polarization in EM spectrum? All the electromagnetic waves. See, all the electromagnetic waves, they do not have elementary particles inside. There is no proton, there is no neutron, there is no electron. All the particles, all the electromagnetic waves, starting from micro to gamma, they can be polarized. Clear? Go to the next one. Sagittarius, is it a stellar black hole? A question. So Sagittarius is a stellar black hole. Basically, we classify Sagittarius as a radio galactic nuclei. So in the mid of galaxy, we have a galactic radio source. Inside the radio source, we have predicted there is a small amount of black hole present. So by the term small, it means it's a stellar black hole. Is it clear? Yeah. Is the polarization clear? Who asked it? Sri Lakshmi. So coming to the next one, AGN, active galactic nuclei. So basically what happens if a galaxy is active? Milky Way does not have a AGN. So in the Milky Way, or imagine any other galaxy, the center is very much active. Basically, it will engulf all the materials that is present around and it will emit a lot of radiation. So that's called as only with accretion disk and gravitational lens we can capture black hole. Yeah, exactly. Without accretion disk, we cannot capture the picture of a black hole. That's why we cannot capture picture of the Sagittarius A. We know Sagittarius A exists, but we cannot capture a picture. That's because it should be excreting materials from nearby. It's not happening. So therefore, we do not have a picture of a Sagittarius A. Clear? A large amount of energy being spewed from the middle, from the small core, it's called as active galaxy. So active galaxy, it can be divided into three types. We have radio, we have quasar, and then we have blazar. Quasar and blazar, these two terms, they were in news repeatedly in the mid of 2020. So if people have been confused about how the accretion works, take a look at this. This is how it works. So basically the light, it bends. So we captured photograph from underneath. This is not the photo which we captured. We captured the picture from the top or bottom of the black hole. So this is the picture of the Pavai which we actually captured. So in reality, it's actually excreting materials from around it. It's basically engulfing materials and some light, it's actually bending from the other places. So this is called as accretion. I'll play it once again. Accretion, basically taking materials from nearby objects, which will include planets, stars, galaxies, anything. This is called as accretion, a very important term. And this disk is called as accretion disk. So basically, we have a picture of the accretion disk of Pavai. And this is a phenomenon mainly because of higher gravitational force of the black hole. So all this excess energy, it will be emitted in the entire electromagnetic spectrum. There is infrared, radio, X-ray, and ultraviolet rays will be emitted from core of the galaxy. I repeat, it is from core of the galaxy. active galactic nuclei. So in the center, in the core, because of the accretion disk, it will emit a lot of electromagnetic waves. Since they are actively excreting, it's called as active galactic nuclei, shortly given in abbreviated form as AGN, active galactic nuclei. The center of the galaxy that is highly active, that is emitting a lot of electromagnetic waves, is called as active galactic nuclei. Clear? Coming to the next one. Don't write the entire thing. So accretion disk is because of the kinetic energy and frictional forces. Write down the second point alone. So when the material falls towards the black holes, it will heat up. The main reason for heating up is the gravitational pull and the frictional force. Because of the kinetic energy, a large amount of heat and radiation will be emitted. Done? So coming to the three types, it's simple. So it depends on the accretion rate. First thing is it depends on the accretion rate. Second thing, it depends on the mass. And third important thing is the viewing angle. So if you're going to view a galaxy, imagine this is active galactic nuclei and it is emitting a lot of radiation. So if you're observing it from a perfectly 90-degree, you call it as a radio galaxy. So imagine you're looking at active galactic nuclei in a tilted form. So somewhere in a different angle, you call it as a quasar. And blazar is basically a top view. So if you're going to look only the top part, it's called as blazar. That's all. So three terms in use. Understand all the three are active galactic nuclei and only the viewing angle varies. To look at this is a quasar. So because this is an active galaxy and it is emitting radiation this way, mildly tilted. So this is what you call as quasar. So quasar, blazar, and radio galaxy, everything is same. It all belongs to active galactic nuclei. Good. Only the viewing angle will vary. We'll go to the next one. Next important thing is TESS. That's quasar. This is blazar. The next one is Transiting Exoplanet Survey Satellite, TESS by NASA. So till you go to the prelims, there will be repeated news about this. I'll tell you why. So basically, they are reading somewhere close to 200,000 stars. Repeat, this satellite is studying close to 200,000 stars, and it will be adding more and more to the exoplanet systems. So it will be adding the number of exoplanets. It will be adding the number of exoplanet system, which will include stars and everything. You don't have to read everything, because right now it has found out somewhere close to 30 or 35 plus planets in star system. We cannot remember everything. If there is any peculiar data about it, you can learn. Good. First one, it's a system by NASA. So it's using a thing called as transient. So what does it mean by transient? Imagine you have a large beam of light. If I'm going to walk in the middle, what will happen? There will be dip in the brightness. You're observing the light from a distant place. If I'm going to walk in the middle, there will be a small dip in the brightness. So similarly, if there's a star, if you keep on observing the star, if there is a periodic dip in the light brightness, we call it as a transient event. It appears for a short amount of time. That's because a planet or something is crossing there. So if it is going to be periodical, then we can confirm it is a planet that is orbiting the star system. So the system is called as transient event. That's why we call it as transiting or transiting. Transiting is a short-term event. Don't write this, write this one. This is called as transit photometry. So if you come across the discoveries of TESS, if there is something like almost the size of sun, almost the size of Earth, it is in a habitable zone. If you come across these three terms, you can learn about it. First thing, almost the size of sun. Second thing, almost the size of Earth. Third thing, it is in a habitable zone or a Goldilocks zone. So if you come across these terms related to the discoveries, you can learn about it. The dip in the brightness is called as transit photometry, basically a short-term and repeated dip in the light. Good. Next one, most recent discoveries by TESS. There are a lot of planets that has been discovered. I'm telling only the peculiar ones. You can write one line about it. Don't write lengthy notes. So it will be followed up by James Webb Telescope and ground-based telescope. This is trivial data. Coming to the first one, these are some of the important discoveries. Talking about the first one, that is Pi Mensae. So Pi Mensae is a star system. So it's important because the star, which is called as Pi Mensae, it's almost the size of sun. The star, which is Pi Mensae, so almost the size of sun. So generally, if this is Pi Mensae is the star, all the planets will be named as Pi Mensae A, B, C respectively. So it goes on. Similarly, HT 21749 is a star. HT 21749 A, B, C will be planets. So it's 60 light years away, relatively closer. Good. Second one. Next we have LHS 3844b. This is important because this is the closest exoplanet system. To the Earth. "49 light years is much closer. And this M-type dwarf stars is also important because we'll be talking about one discovery by IAA, Indian Institute of Astrophysics, physicist. M-type dwarf stars. Numerically, they are supreme because most of the stars which we know are M-type dwarf stars. Next one, HT 21749. So HT 21749 is again closer, somewhere close to 53 light years. So HT 21749 is the star. HT 21749A, HT 21749B, HT 21749C. It's exoplanet with 3 planets. And third one is important because the third planet is almost the size of Earth. It has a diameter of around 89% of the Earth, which means it's almost the size of Earth. HT 21749 is the star. HT 21749A, B, and C, all the planets were confirmed by TESS. And C is important because the size is almost equal to the Earth. Coming to the next one, one of the tiniest planet discovered by TESS. It's called as L98-59. So size somewhere between Mars and Earth. No more detail is required. One of the tiniest planet discovered by TESS. If it's not clear, L9859b. So this is Earth, this is Mars. It's an intermediary sized planet. All these are discoveries in 2020. So learn one line about it. This is sufficient. And after this, I think they were tired of naming. They started naming it as TOI, Test Object of Interest. That's all. We're not keeping names to the planets anymore. It's called as TOI, Test Object of Interest. So TOI 270 is very much important because the peculiarity is generally, if there's a star, the planets will be at a much longer distance. For example, the closest planet, Mercury itself, is much longer, located at a much longer distance from the sun. But if you see, all these planetary system, especially this TOI 270, it's much closer. All the 3 planets, they are closer to the star, comparable with Jupiter and its moon. If you take Jupiter as TOI 270, the moons are its planets. So basically, there is a possibility that planets can orbit much closer to cool stars. 3 planets orbiting the host star at a much closer distance, lesser than the distance between Jupiter and its moons. And then GJ357. And this GJ357b is important because it's called as super Earth. Because the temperature is high, but its mass is equivalent. It's found to be equivalent to Earth. Next is, I told you, TOI. It has B, C, and D. The star is here, and all the planets are much closer. GJ357. In that GJ357d is BB. This one is important. This is called a super Earth. GJ357b is also called as super Earth or hot Earth. The mass and diameter were found to be much closer to the Earth. Now I'll ask a question. So it's possible for a planet to orbit 2 stars. The question is, it's possible for a planet to orbit 2 stars simultaneously, true or false? We have a sun and we have 8 planets around the sun. So is it possible that a planet orbits 2 stars simultaneously? That's a question. True or false? Archana says false. Any other answer? 2 stars and the planet should orbit the star. Yes, it is possible. And those planets are called as circumbinary planets. Good, circumbinary. So basically 2 stars orbiting each other and then a planet orbiting the star. So that's called as circumbinary planets. Test object of interest 1338. This is important. It's called as eclipsing binary. There will be regular stellar eclipses. So this is not the first time that a circumbinary planet was discovered, understand. Even we have 10 plus circumbinary planets that has been discovered by other systems. This is just adding the number of circumbinary planets. Yes, in astronomy, it is possible that one planet can orbit 2 plus stars, more than 2 stars. Those are called as eclipsing binary. This is just for your basic understanding. This is how it works. One star,
it's nearly the size of Saturn and orbits its stars every 95 days. The 2 stars orbit each other and consist of by looking for tiny regular dips in starlight called transits. Tests saw TOI 1338b's transits of the large star, but spotting them in the data wasn't easy. A high school intern examined hundreds of eclipsing binaries to search for planetary transits, which can look similar to some of the eclipses. Ultimately, he uncovered transits caused by the planet. If you could
One
orbit
planets by the
TOI
planet, other planets by the star.
1338b, you'd have a front row seat to see its suns eclipse each other every 15 days.
That's how this was discovered. And the next one is TOI 700. So in TOI 700 is special. What is meant by a stellar eclipse? So eclipse caused by the star. We have solar eclipse means eclipse caused by the sun. We have lunar eclipse means eclipse caused by the moon. And then we have stellar eclipse, which is an eclipse of the star caused by other star. That's called a stellar eclipse. If eclipse is caused by moon, we call it as lunar eclipse. If it's caused by the earth, it's called as solar eclipse. And if eclipse is going to eclipse of the star going to be caused by another star, that's what you call it as stellar eclipse. Is it clear? So this is important because most of the stars, exoplanets that we discovered, the planets were either too close or they were too far. So imagine they were something like Mercury or they were something like Neptune or Pluto. So we did not have planets in the exoplanets that were in the habitable zone. So these are called as Goldilocks zones. Earth is in Goldilocks zone, which means it has surface water for the organisms to thrive. So if it's going to be closer to sun, the water will evaporate. If it's going to be away from the sun, the water will be frozen. There won't be surface water. But if it's in optimal distance, it will have surface water ready for consumption. Those zones are called as habitable zones or Goldilocks zones. For the first time, HT 700, there's a planet called as TOI 700d. So this is present at the Goldilocks zone compared to TOI 700. Optimum distance away from the star. The first planet to have or to be located at the habitable zone of a star. Clear? We'll go to the next one. And next we have a system similar to a planetary system, but it's formed solely because of stars. Basically 6 stars, 6 binary stars orbiting each other. This arrangement is called as sextuple system. So imagine 6 binary stars, the stars orbiting each other. Such system is called as sextuple system. This is the first sextuple system that was ever discovered. Basically consists of 6 stars or 3 set of binary stars. Yes. The next one, the last one is TOI 451 system. So this is the most recently discovered. So this is important because TOI 451 is a young star. It is compared to Sun. TOI 451, you can write it, it is almost similar to Sun. It's called as younger Sun. That's all. This is sufficient. Read 1 or 2 lines about anything that's being discovered by TESS. Don't dwell deeper. Because as I told you, 200,000 stars being monitored and they constantly updated. Once or twice in a month, you have always some news about the exoplanets. So coming to the next one, Tau-Bute radio burst. Tau-Bute. So Tau-Bute is an exoplanetary system. For the first time, we have discovered something called as a radio burst. What is special about it? The main thing is, generally, we don't get radio burst from the planets. This is the first time we are receiving a radio burst from a planet, which confirms the magnetic field is strong, and there is a possibility that it has atmosphere. That is the main discovery. First ever radio burst from a planet. located 51 light years away from the Earth. We have never received a radio signal from any other planet. So this is the first time we are receiving a radio signal. There were fancy clickbaits like, are aliens sending a signal and anything? No, it's not about aliens. More research is underway. It could be because of anything. Good. So the main reason for studying radio source from a planet is basically we can check what is present inside the atmosphere and what is present underneath the surface. So basically for atmospheric topographic studies. And most important thing, these radio bursts, it occurs for few milliseconds only. And radio waves, they are produced only when they have changing magnetic field. Write this and this. This may not be necessary. Read it once. Write down these 2 points alone. So for now, we have discovered a fast radio burst from Tau Bote. Other than that, we have discovered fast radio burst from neutron stars. We'll read about it next. Done? Clear? So magnetars, very important. So coming to magnetars, imagine now we are not going to talk about the low massive stars. We are going to talk about high massive stars. The high massive stars, I told you, if the mass is somewhere between 1.4 times the stellar mass or solar mass, or between the 3 times the solar mass, it will form neutron stars. So there is a subset of neutron stars called as magnetars. Good. So magnetars, they are much smaller than neutron stars, but at the same time, field is extremely high, much higher than the neutron star. So they are subclass of neutron stars. They have ultra powerful magnetic strength. Now my question is, are there magnetars in Milky Way? Take a random stance. Are there magnetars in the Milky Way? Is there a possibility that we have magnetars which are super powerful neutron stars with multiple times, which is multiple times stronger than neutron stars? Sri Lakshmi says yes. Okay. Any other answer from the 20 people present here? Yes, there are around 10 magnetars in the Milky Way. Good. So if you get a statement saying magnetars are neutron stars with ultra powerful magnetic field, there are no magnetars in Milky Way. If there is any statement like that, understand there are magnetars. There are around 10 magnetars in the Milky Way. So as a part of it, NASA recently told it has received a mix of X-ray and radio wave burst from magnetars. So it's called SGR 1935. That is not necessary. Don't worry. But understand, magnetar are types of neutron stars. That's all. They're not black holes. They're not white dwarfs. They're not black dwarfs. They are basically a subclass of neutron stars. Yes. So next, a common question. So smaller the size of star, more is the possibility of inhabiting it. I'll repeat the question. Smaller is the size of star, more is the possibility of finding a planet that could be inhabited. True or false? Smaller the star, more is the possibility of finding an inhabitable planet. True or false? Based on what we learned till now. True. Okay. So Bigger ones are unstable. Yes, the bigger ones are unstable. So all these days, people were thinking, the scientists were thinking, there is a subcategory called as M dwarf star. I was telling you, M dwarf star, basically it is much cooler and it's smaller in size. Understand, M dwarf is smaller in size, lesser in mass compared to sun. So it has somewhere between 8 to 50% of mass of the sun. So which means M dwarf stars are much lighter and much cooler. So there was a misconception that M dwarf stars cannot be inhabited. Good. So based on the recent study from the scientist in TAF, Tata Institute of Fundamental Research, and from the data received from Himalayan Chandra telescope, what we have discovered is we have developed an algorithm that could be used for studying about M dwarf stars. And they are saying if M dwarf star, it is closer, that is, it is in proximity, and there is a greater possibility of inhabiting it. That's the most recent discovery. Okay, before we wind up, go to the next topic. See, magnetars. Other than magnetars, we have something called as pulsars. So if magnetar is basically a single neutron star that is emitting magnetic field, no light, only magnetic field, high amount of magnetic field. So if the neutron star is going to emit a lot of radiation, like this beam of radiation, you call it as pulsar. So we have magnetars, we have pulsars, and then we have magnetar pulsar, which means it emits a lot of magnetic field as well as radiation all together. So there are three categories. One is magnetar. Second thing is pulsar. Third thing is magnetar plus pulsar. These are the three types or subcategory of neutron stars. And in the last 1 or 1.5 years, we had news only about magnetars, nothing about pulsars, nothing about magnetar pulsars. Good. The next one. The neutron star is called as SGR 1935, if you want to note down. The recent discovery by NASA scientists. It's somewhere close to 14,000 to 41,000 light years. It's called as SGR 1935. It's not exoplanetary system, it's a magnetar. Don't write this, but I'll tell you for a comparison. Imagine the sun's magnetic field on an average when it reaches Earth, it's somewhere close to 5 Gauss. Gauss is the measure of a magnetic field, wherein there will be million to billion Gauss in the magnetar. So imagine the amount of magnetic field it will be having, extremely high amount of magnetic field. Good. SGR 1935 is the name. Coming to the next one, we were talking about M dwarf stars. Much important. Sun is yellow dwarf star, wherein M dwarf stars are even more lesser. It's 8% to 50% the sun mass of sun, and they are numerically supreme, which means 70% of the stars which we know in the galaxy are composed of M dwarf stars. Done. And the next one, read it, don't write it. Possibility of Earth-like planets, appearance of Earth-like planets. The possibility increases when the stellar mass or radius decreases. If you want to write it shortly, you can write it as stellar mass is inversely proportional to finding an inhabitable planet. So stellar mass and radius, it is inversely proportional to finding an inhabitable planet. Lesser the mass, more is the possibility. Good. Next one. Don't write this. Read it once. So we have discovered new parameters about M-dwarf star that could identify if they are potentially habitable. So this is basically a discovery by Indian scientists, and they have studied about 53 M-dwarf stars, basically using TFR, Tata Institute of Fundamental Research Spectrometer and Imager, and Himalayan Chandra telescope. I'll be giving an introduction about these telescopes in the next class after the break. Good. Next one. So Biba and Santa Massa. This is important because, see, basically, I told you the naming of the planets and stars. It's because it's generally approved by International Astronomical Union, and right now they have named one planet and one star behind the names of Indians. One is called as Biba, the other one is called as Santa Massa. Biba is much important because you can add it to the contributions of Indians in the field of science and technology. Because Biba Chowdhury is the lady who discovered pi mesons, which is a subatomic particle, not elementary particle, subatomic particle, basically building blocks of elementary particles. Two things. The star is called as Biba, the exoplanet is called as Santa Massa. As I told you earlier, don't write about Kalpana Chawla or Sunita Williams, Rajachari, or Swati Mohan, all these people in the contributions of Indians in science and technology. They are people of Indian origin. We'll go to the next one. So next is Betelgeuse. Betelgeuse. This is important. Whenever you see this term, Betelgeuse, remember this is a star. So this is located somewhere close to 725 light years away from Sun. So we have been closely following the star for the past 2 years, starting from 2018 till 2020. Because in 2018, what happened was this Betelgeuse, it lost its brilliance. Somewhere close to 2/3 of its brilliance was lost. And this is a supermassive star, not a normal star. It's a supermassive star that is located 725 light years away from the Sun. So we expected, since it's losing its brightness, we thought it's going to undergo supernova explosion. If that happened, this would be the first supernova explosion to be recorded from Earth. So that is what we expected. But what happened was in 2020, again, it gained its brilliance. So supernova explosion did not take place. Rather, it gained its brilliance. So the main reason was the first thing, the dim in the brightness. It was not because of the supernova explosion. It's actually because there were dust clouds around the Betelgeuse. First thing. Second thing, the outer layer, it underwent expansion. So because of that, there was dimming and then it regained its brilliance. And also there was a scientific article explaining what will happen if the supernova explosion happens somewhere close to 725 light years away from Earth. The answer is there is no damage to us. I repeat, there is no damage to us. Even if the Betelgeuse is going to explode, we won't be affected. The thermal radiation will not reach us. Clear? 725. It was there on Feb 14th also. The Indian name for this is called as Kakshi. We can see it with naked eyes, even though it's located away, like 725 light years away. Since it's a supermassive star or a red supergiant, if there is lesser light pollution, we can see it from the Earth without telescope. Good. Coming to the next one. So it's a result of something called a stellar pulsation. So basically expansion and contraction of the outer layer, it's called as stellar pulsation. The star is not undergoing supernova explosion in another 100,000 years. That's what we have predicted now. For another 1 lakh year, it will not undergo supernova explosion. Okay, the next one, we are going to talk about planets. Not planets, it is planets. Any idea what is meant by a planet? Something like a planet, but not a planet. So to explain this, I'll ask a general question. Whenever a planet approaches closer to its star, I'll repeat, whenever a planet approaches closest to its star, the number of moons will reduce, true or false. The number of moons may reduce, we'll keep it like this. Whenever a planetary system approaches closer to its star, the number of moons may reduce, true or false. People online? True. Okay, so there will be a gravitational jolting, because imagine the Earth is there. Suppose it reaches the position of Venus, or somewhere it reaches the position of Mercury. What will happen is the gravity will increase. So when the gravity increases, the force of gravitation between the sun and the planet is going to increase, and there will be a gravitational jolting. When it's trying to strike a balance, mostly the moons will be ejected. It will be ejected away from the path. It will be set free. So all these orphaned moons, they are called as planets. It's a new term. So planets are basically orphaned moons, basically formed because of the gravitational jolting, which generally appears when planets get closer to the star. Detached moons or orphaned moons. Clear? So this picture explains how it happens. The planet approaches closer and the moons are detached. Those are called as planets. And the next thing, did you ever come across this term called as Oumuamua? Really weird sounding name. It's a Hawaiian name. So did you come across this term called as Oumuamua? This was this incident. It happened in 2017. And all these 3 years, there are different theories for this incident. Can someone say what is meant by Oumuamua? Okay, so to answer this, first I'll ask a question. Asteroids are part of solar system, true or false? Definitely yes, they are somewhere found between the Mars and Jupiter. There are Trojan asteroids and then there are near-Earth asteroids and everything. They are part of the solar system. And comets also enter the solar system. They are away from the solar system, which are generally formed in Oort clouds, but then they enter the solar system. So other than that, we do not have any interstellar object that has ever entered into the solar system. So I repeat, other than the comets which are from outside the solar system, we do not have any other interstellar object that has ever entered the solar system. For the first time, a large cigar-shaped object. Imagine a cigar-shaped object, and the elongation ratio was 10:1, which was much longer. This is not asteroid because it did not have dust on the top. And also, it's not comet because there was no ice on the top. So basically, it's an unknown type of object that approached much closer to the sun, and then it took a turn, and then it's traveling to the Pegasus constellation right now. So probably the first ever, it appeared like a alien object, like a flying saucer. So there is consistent theory about this Oumuamua repeatedly in the newspapers and different scientific papers saying this is the first alien visit and everything. So learn a little bit about it. First interstellar object to enter the solar system. This is an artistic impression. First interstellar visitor. And this is also extremely important because we all know that sun has extremely high amount of gravitational field. But the sun was not able to control it. It was not able to slow it down. And it did not trap it inside the solar system. So it approached at a greater speed and then escaped. It was a quick visit. So in few scientific papers, they called it as light sail because it approached at a much larger velocity. Even sun cannot capture it. So this was called as a light sail. Point number 1 to write down, point number 2. Don't write this. Read about it in your notes. Write this point and this point. Yes, done. So an animation on how it actually happened. See, this is the solar system. It made a closer approach. It made a flyby. And right now it's traveling somewhere to Pegasus constellation, a collection of stars. This is all we know about it. But it's a hyperbolic path. Don't write it. You can write about this one alone. So it was captured by Pan-STRASS. So it's a Hawaiian telescope. Yes, done. Next we have, I think one part is over. Yeah. So next we'll be learning about all the ground and space-based observatories that are generally observing the astrophysics events. I think the second class will be relatively shorter today. Good. So the first part, first most important thing is NASA's space observatories, or also called as great observatories. So basically, there are four great observatories, out of which two has been deorbited. So this Compton X-ray observatory. So sorry, the Compton Gamma Ray Observatory, and the other thing was deorbited. That is Spitzer. Spitzer was deorbited much recently in the last year. So right now there are only two space observatories which are part of NASA's Great Observatory program, and right now they're planning to upgrade it with something called as James Webb Space Telescope, which is very much advanced space telescope, which will be launching in the mid of 2021. And similarly, which is the only space-based observatory of India, means there is only one thing that's called as AstroSat. It's not a collection of telescopes, it's basically a single satellite. AstroSat is the only space-based telescope of India. Remember, even though there are many other observatories like Hubble, Chandra X-ray Observatory, and everything from different countries, India has only one space-based observatory that's called as AstroSat. I'll give a basic introduction about it, and then about NASA space observatories, and then about LIGO, the Laser Interferometer Gravitational Observatory. So first thing, the series of four space-borne observatories: Hubble, Compton Gamma Ray, followed by Chandra X-ray, and Spitzer Space Telescope. Chandra X-ray Observatory is not to be confused anywhere close to Chandrayaan. It's a totally independent one. It's by USA. Also, this is not to be confused with the Himalayan Chandra Telescope, HCT. Himalayan Chandra Telescope is a ground-based observatory by India. It's located in Hanley in Himalayas. We'll be reading about it. Chandra is in space. That's by USA. Himalayan Chandra is by India. That's located in Himalayas. A basic introduction to all of these. First one, talking about Hubble. Hubble is very much important because it has contributed to most number of scientific papers. It's still functional, not going to be deorbited in near time. Three important data about Hubble Space Telescope. The first thing, it can read the electromagnetic spectrum starting from ultraviolet rays till infrared. So ultraviolet, visible, and infrared. All these things, it can be studied using Hubble Space Telescope. And second thing, it is located at low Earth orbit. It's not located at medium Earth, or it's not located at high Earth orbit. It's located at low Earth orbit, somewhere close to 500 kilometers above Yeah, I hope the video and audio are clear now. So the main reason for using multiple space observatory is this way. Basically, we want to observe all the events, astronomical events that are happening in different electromagnetic waves. This gives an idea about the different space-based observatories that's being used by NASA, mainly USA. We have Fermi, Chandra, and everything. So in this, the Great Observatory Program, it's formed by 4 telescopes. So Compton Gamma Ray, Chandra, Hubble Space Telescope, and Spitzer, out of which only these 2 are presently operational. These 2 are deorbited now, I told you. So talking about the first one, it observes from ultraviolet till infrared. And I told you it does not have thrusters. The main reason for not having thrusters is, basically it's observing in visible light also, which means if there is any obstruction in the light that's coming into the telescope, then the readings are not going to be clear. So if the telescope is going to fire fuels based on fuel and oxidizer combo, what will happen? It will generally obstruct with the observation. So to do this, they're basically using only 2 principles. The first thing, there is a spinning wheel inside. So which means it's going to use 2 things. One is conservation of angular momentum. Second thing, Newton's third law of motion. For every reaction, there is an equal and opposite reaction. So based on these 3 principles, it is working. So the main idea behind this is conservation of angular momentum and Newton's third law of motion. So basically, if you spin a wheel, which is present inside the Hubble Space Telescope, if the wheel is going to be tilted, the telescope will move in other direction. So without any fuel, without any radioactive fuel, or without any fuel and oxidizer combo. So take a look at this. Let's say we have a spinning wheel, and then you put it this way, it'll spin in this direction. You put it this way, it'll spin in this direction. So the same principle. It's basically the wheel spinning part. It's called as conservation of angular momentum. You can read about it in the NCERT once again. The force possessed by the objects towards the center, spinning objects towards the center. So basically, angular momentum is conserved. And in the direction of tilt, you will move in the opposite direction. So this is called as a combination of conservation of angular momentum and the Newton's third law of motion. By these combination, the Hubble Space Telescope will alter itself. If it wants to change the direction or orientation or anything, it will be using. So one common question which people ask is, if there is a very simple way like this, and why do we put ion thrusters and everything inside the satellite? But understand, this can be used if you want a slower turning. For example, the Hubble Space Telescope takes somewhere close to 15 minutes to turn 90 degrees. So imagine if you want to make any collision avoidance or maneuver or anything, it's going to be difficult. So if you want to move really, really slow, if it's fine, the turning speed is fine, then we can use this methodology. So basically, I told you there are no thrusters. It employs only spinning wheels. Clear? Second one, that is Compton Gamma Ray Observatory. So we'll finish the Great Observatory Program and then go for a break. Clear? Compton X-ray Observatory, it was deorbited in 2000, and the most important finding is terrestrial gamma ray flashes, TGF. So Compton Gamma Ray Telescope, it confirmed that thunderstorms will cause gamma ray flashes. So gamma rays, they are highly energetic. I told you it's on the extreme right end of the electromagnetic spectrum. So thunderstorms, they can cause gamma ray. I'll ask a general question. So we all have lightning arresters. So the building, we have lightning arresters that will neutralize the charge. So which charge is being neutralized? Is it the positive charge or is it the negative charge? Which charge is generally neutralized by the lightning arresters? Is it positive or is it negative? Most probable answer, negative. So generally we neutralize negative charge. So which means if we have a cloud that's causing thunderstorm, negative charge is present at the bottom and positive charge is present at the top. So when these are neutralized, there's a possibility that it creates gamma rays. Take a look at this.
Deep within their roiling clouds, thunderstorms hold an elusive surprise. Under just the right conditions, they produce some of the highest energy radiation naturally found on Earth, terrestrial gamma ray flashes, or TGFs for short. Studies by NASA's Fermi Gamma Ray Space Telescope have shown that TGFs fire up about 1,100 times a day. Now, new research combines Fermi detections with ground-based radar and lightning location data. These studies show that TGFs come from more diverse types of storms than previously thought. In a thunderstorm, collisions among rain and snow cause different parts of the cloud to develop positive and negative electrical charges. When the strength of the electric field overcomes the insulating properties of air in the thundercloud, a lightning flash occurs. Most lightning occurs entirely within the cloud and is called an intra-cloud flash. All lightning produces a strong and sudden change in the storm's electric field, but the upward portion of an intra-cloud flash sometimes sends a surge of electrons rushing toward the upper part of the storm. Reaching speeds nearly as fast as light, these accelerated electrons give off gamma rays when their paths are deflected by air molecules. Using global lightning location networks, scientists can determine the TGF position more accurately than with Fermi data alone. 24 localized TGFs occurred within areas covered by next-generation weather radar systems. This gives scientists the opportunity to begin studying the kinds of storms that produce TGFs. These slices of radar data capture different types of storms encompassing a wide range of updraft strengths. Even the weakest of them produced a TGF. Another finding, TGFs seem to occur in the same altitude range, between 7 and 9 miles high. Lightning can form at much lower altitudes, so there's every reason to think TGFs can too. But gamma rays from TGFs occurring deeper in the atmosphere are greatly weakened. They're too dim for Fermi to detect, which probably means the satellite is undercounting them. TGFs may be far more common than we think. With this knowledge, scientists can design experiments to track storms and study how TGFs relate to their strength and evolution. This will give us an even better understanding of planet Earth's most powerful natural particle accelerator.
So based on this, you can expect questions somewhat like this. A surge of electrons can cause gamma ray flashes. Yes, gamma rays last for a few milliseconds. It can be produced in thunderstorms. Because whenever we think about gamma rays, we always think about radioactivity. We have alpha rays, beta rays, and gamma rays. So gamma rays are highly ionizing radiation, which are generally found in stars and galaxies and everything. But understand, even on the Earth, even by the thunderstorms, there is a possibility that gamma rays are produced, but they are produced at, as a flashes for a much smaller time. Good. So TGF, it lasts for less than one in thousandth of a second. Don't write the entire thing, write the first line alone. So this is a subtopic in Compton Gamma Ray Observatory. We are yet to read about Chandra and Spitzer. So TGF, it generally lasts for less than 1 in thousandth of a second, and most importantly, the avalanche of electrons, they'll go at higher speed, when electron is traveling at a higher speed and then it gets deflected by air molecule, it will give out gamma rays. That's all. This is the overall idea. So deflecting fast moving electrons can produce gamma ray flashes. This is the overall idea. Deflecting fast moving electrons, it will produce smaller gamma ray flashes. They're not powerful, but still they're gamma rays. Coming to the next one, Chandra X-ray Observatory. So the main reason for observing X-rays in the universe, see, whenever there is, so whenever there is high temperature, first one. Second thing, whenever there is high gravity. Third thing, whenever there is high magnetic field. If these three things are there, generally X-rays will be produced. In all the astrophysics events where temperature is high, where gravity is high, wherever the magnetic field is high, it will produce extreme high amount of X-rays. So for reading these, we needed a telescope, and that's called as Chandra X-ray Observatory. It's located in high Earth orbit. Understand, one of the great observatories that was located in high Earth orbit. So for observing objects such as black holes, quasars. I told you what I mean by a quasar, basically active galactic nuclei that is tilted. All the high temperature gases, they'll be in X-ray portion. And relatively low temperatures, it will be in infrared portion. High temperature is the keyword, because for all the high temperature phenomenon, we'll be using X-ray observatory. And for all the low temperature phenomenon, we'll be using infrared observatories. Good. And the next one, so I told you already, whenever there is high magnetic field, high gravity, and high temperature, generally it has X-ray. Don't write this. You can write this alone. So it can detect objects that are swirling as long as 90 kilometers away from the event horizon. So X-ray is one of the prime source of detecting black holes. Done. The last observatory, that is Spitzer Space Telescope. So as I told you, this is an infrared telescope. So basically for reading all objects that has much lesser wavelength or lesser temperature. The most important thing, it cannot penetrate the Earth's atmosphere. So it will be absorbed. All the heat radiation will be absorbed. So we cannot read infrared related data from the surface of Earth. We have to be above the surface of Earth. There are two important observatories that are repeatedly in use. One is Spitzer Space Telescope and write down plus SOFIA. Read about SOFIA after the break. Spitzer and SOFIA. So the Lumen 16A, which we were talking about, for all other detections, SOFIA was playing an important role. Clear? So we'll stop here. We'll take a break. We'll take a break for half an hour, which means we'll start the class by 5:10. Maximum the class will go on up to 7:10. I think we'll be having a short break for 5 minutes. We'll be finishing by 7:10, in and around 7:10, right? So I'll meet you by 5:10. Till then, the online people, I'm watching your messages. If you have any doubts, you can drop your messages here. I'll be available for answering. Yeah, I hope you people are back. We'll start. Okay, we were talking about the great observatory program of NASA, which is composed of 4 main observatories. Yeah, so I told you it's Hubble Space Telescope, which contributed to 20,000 plus scientific papers, which could capture in infrared, visible, and ultraviolet rays. And then we were talking about Compton Gamma Ray Observatory, which is actually confirmed the terrestrial gamma ray flashes and different phenomena. And then about Chandra X-ray Observatory, not to be confused with Himalayan Chandra Telescope, which could actually capture high energy thermal events and high gravity and high magnetic field events. And then we were talking about the Spitzer Space Telescope, which was deorbited in 2020. Basically, it could read in infrared radiation. It could read the infrared spectrum, which is generally produced by faint stars or low radiation fusion and everything. Good. And then we are going to talk about SOFIA. SOFIA is very much important because SOFIA is considered to be one of the marvels of science. I'll tell you why. So when it comes to infrared, so all the living organisms, they emit infrared rays. For example, we emit infrared rays. Imagine the famous movie called as Predator, where the alien will see us in a green color shade. So basically, or even if you have looked at this all National Geographic channels and everything, whenever the snake is hunting a rat, it will be a black color screen with just the rat appearing like a red color. So basically, all the night visions and everything, it employs infrared. So the thermal radiation that's emitted from the organism's body, it's generally mapped. So that's how infrared camera and everything works. But because of the presence of atmosphere, most of the infrared is observed. So whatever infrared radiation that are coming from outer space, it's generally absorbed in the atmosphere. So for this reason, we cannot read about infrared events that are happening outside the Earth from inside the Earth. So basically, ground-based observatories cannot read infrared. So for this reason, they can read infrared, but not accurately. So for this reason, we generally place space-based telescope, wherein SOFIA is intermediate between space-based telescope and ground-based telescope. Basically, this is a Boeing 747, which is modified with a telescope placed behind it. So it's a partnership between NASA and German Aerospace Center. SOFIA is the abbreviation for Stratospheric Observatory for Infrared Astronomy. So it has a telescope which is carried by an aircraft. So it covers a spectrum that's not possible by ground-based observatories. That's the main important thing. The prime purpose is we are covering infrared spectrum that cannot be covered by ground-based observatories. So this is SOFIA 747 that has a huge telescope inside. So generally it flies in the night time where noise and light pollution is much lesser, and generally it flies above the Antarctic and Arctic region. So generally we use it for studying all the transient events and infrared events. It will fly somewhere above 35,000 feet above the Earth's surface, which means it will try to capture the infrared events that are above the Earth's surface. Some of the important contributions. So it studied eclipses like events of Pluto, Saturn, Moon, and Kuiper Belt object called as MU69. This one is important. It's called as Arroco. Done. Coming to the next one, we are going to talk about gravitational waves. So understand gravitational waves are different from the force of gravity. Good. We're going to talk about gravitational waves. Good. The first thing, what produces gravitational waves? Waves are just like water waves. We have gravitational waves. So the main reason for producing gravitational waves is accelerated particles. So whenever an object spins at a faster rate, or when it orbits at a faster rate, it creates a ripple. So those are called as gravitational waves. So they're ripples in space-time. So created by mass moving objects with extreme acceleration. So imagine a neutron star is spinning at a faster rate, then it will create a ripple. So those are called as gravitational waves. This is not to be confused with the gravity force. This is just waves. Just like electromagnetic waves, we have gravitational waves. So merger of black holes or merger of neutron stars, all such cataclysmic events or colliding events, they'll create gravitational force or gravitational waves. Coming to the next one. So a simulated video of how it happens. See, these are two neutron stars. So once they come close to each other, what will happen is they'll start spinning faster and then they'll merge. I told you neutron stars are generally binary units. So generally there'll be two neutron stars that are orbiting each other. So when they get closer to each other, what will happen? The kinetic energy will increase. Just like how protostars are formed, the kinetic energy increases. The massive object that is spinning, it creates ripples. So these ripples are called as gravitational waves. So sensing the gravitational waves, it can give us idea about fusion of neutron stars or fusion of black holes and everything. Good. So we have a experiment called as LIGO, Light Interferometer Gravitational Observatory. So it's actually doing this work. Now, based on the type of merger, we have different types of gravitational waves. The first is continuous gravitational waves. Then we have stochastic, which is generally a normal gravitational wave, and then we have other type of gravitational wave. So before we talk about it, first thing I'll ask a question. We are talking about binary systems. Question number 1: two neutron stars can form binary system. True or false? Two neutron stars can form a binary system. True. Two black holes can form a binary system. True or false? Two black holes can form a binary system. Some say is true, some say is false. Okay. Third, yes? False. Okay. Third question. A neutron star and a black hole can form a binary system. So two neutron stars can form a binary system. The answer is true. The second question was two black holes can form a binary system. Most of the answers were false. The third one is one neutron star and a black hole. They can form a binary system. True or false? Most of the answers being false. The answer is, for all the three, the answer is true. We have different binary systems. Binary means basically two systems. It's possible that two neutron stars orbit each other. It's possible that two black holes orbit each other. And it's possible that a single neutron star and a single black hole orbit each other, and then they undergo a merger. Good. So if it is going to be a two neutron star, or if it's going to be a two black hole, or if it's going to be a neutron and black hole binary, we call it as in-spiral gravitational wave. The first is continuous gravitational wave, which is generally formed when a neutron star is fastly spinning. Then we have in-spiral gravitational wave that is generally formed because of binary system. The last one is stochastic gravitational wave, which is generally detected, but we don't know the source. So 3 types of gravitational waves. First is continuous. So they're produced by rapidly spinning single object. I repeat, it is formed by a single object. It's generally formed by single spinning object. Best example is neutron star. If you remember the magnetars, they will emit continuous gravitational waves. I told you magnetars are a type of neutron stars that are much smaller in size and they have high magnetic field. So they possibly will emit gravitational waves. Continuous gravitational waves. And the next one, in-spiral gravitational wave, which is generally formed because of a binary system. So far, all the waves detected by LIGO experiment, it is from binary system. So when 2 neutron stars or anything is merging, it will form in-spiral gravitational waves. We have 3 combinations: binary neutron star, binary black hole, and neutron star and black hole binary. 3 different types of systems. So for all the objects that were detected by LIGO experiment, they are compact binary in-spiral gravitational waves. So Shivapriya, you asked about the NCERTs and relevant topics. I'll tell it in the next class. I'll give you a basic idea for what to read and what not to read. Coming to the last one, stochastic binary gravitational waves. They're random and we don't know their exact source. Show the previous slide. Okay. The first ever detection made by LIGO was a binary black hole merger. So this was asked in 17 UPSC. Recently, the merger of black hole was detected. What is the outcome of it? More recently, LIGO has detected a binary neutron star merger in 2019. So coming to the next one, LIGO. So laser interferometer, gravitational wave observatory. So before that, I'll give you basic introduction. First is called as laser interferometer. So first thing, what is mean by interferometer? Can someone say? In physics in 11th and 12th standard, you would have read something called as interferometer. Even if there are engineering students from EC background, you would have read something called as interferometer. Can someone tell what is mean by interference in light? We have reflection, refraction, polarization, diffraction, and interference. 5 important events. So if there is an object, say a mirror or something, light is getting reflected means it's called as reflection. And then when light is passing through a transparent medium, if it's going to bend, it's called as refraction. So basically bending of light. Then we have interference, and then we have polarization. I told you what is meant by polarization. Polarization is in different planes. You pass through a polarizing filter, only one plane emerges out. That's called as polarization. Now, what is mean by interference? Anyone from addition of wave patterns? Okay. Archana says it's basically addition of wave patterns. Good answer. What if I say there are two types of interference. One type is constructive, the other type is destructive. So Archana's answer is basically constructive interference. Good. See, imagine we have water waves. You drop a stone inside a pond. What will happen? It will form a first ripple. And then there will be another ripple. So at some points, these ripples will meet and the height of the wave will be more. Sometimes the height of the wave will be less. So this is called as interference. Basically overlapping of two waves, and the resultant is called as interference. And we can say two types. One is constructive interference and the other one is destructive interference. Imagine you have one wave like this. You have other wave like this. Good. Point number two, you have one wave like this. You have other wave like this. Point number one, point number two. This is case one, case two. So which one will be more intense? Can someone say, is it number one or is it number two? Easy one from the visual, you can say. Yeah, which one is going to be more intense? It is one, because when one wave reaches high, other one is also reaching high. So they are in phase with each other, they are coherent, they are oscillating in the same phase. So this is called as constructive interference. Imagine the high value is 5. So the total high value of this one will be 10. Wherein here it is plus 5 and minus 5. The total value will be equal to 0. So basically when the light or any wave adds up, you call it as constructive interference. When they cancel out each other, it's called as destructive interference. So we are going to use this phenomenon for detecting gravitational waves. Now the question is, how can we use constructive and destructive interference for detecting gravitational waves? Understand? So gravitational wave, there is a peculiar characteristic which we cannot feel. What happens when gravitational waves pass through us? Basically, it will stretch out particles. Imagine a particle is like this. What will happen when gravitational will pass inside? First time, it will be compressed. Second time, it will be stretched. Again, it will return back to normal position. This is position number one. This is position number two. This is the characteristics of gravitational waves, but we cannot feel it because the gravitational waves from neutron stars or anything is too weak to cause change in us. We are too heavy to take up the gravitational waves, so we cannot feel it. But minute things, we can feel this change in width and length of it. So using this, we are determining if gravitational waves are present. This is the overall idea. I'll show you a video. Before that, you can write basic definition. So interferometer, basically it's going to merge two sources of light. And depending on the interference pattern, we are going to check if gravitational waves are present. Coming to the next one, the basic principle of interference. I told you two types of interference. So the first one is constructive interference. The second one is destructive interference. You can draw a rough diagram for your understanding. The waves adds up, it's called as constructive interference. The wave will be bigger, the brighter, and it will be more intense. And then we have destructive interference. This is an example of interference where a single event causes two different ripples. You could see the overlap of the waves. So this is an interference pattern. Basically, the waves will be high whenever two waves, the highs of the wave meet. That's the overall idea. And this is the instrument that's going to be used. I'll tell you how it works. So I told you, even in Earth, gravitational waves are going to pass. What should happen? The Earth should stretch out like this, and then it will stretch out like this. But this amount of stretching will not happen, but it will happen in a very minute scale, ultra minute scale to few pico or nanometers. So we have to detect this change in length and breadth of an instrument. So what we are going to do is, we are going to use two arms being placed parallel to each other, sorry, perpendicular to each other, basically 90-degree apart, and each of them will be 4 kilometers apart. I repeat, each of them will be 4 kilometers. So what we are going to do is, we are going to send a laser beam. The laser beam will be split. First laser beam goes here, and second laser beam goes here. 4 kilometers apart, there will be a reflector. I'm drawing a very simple diagram. Good. So the first beam, it goes here and then reaches back here. The second beam, it goes here and reaches back here. Both of them, when they come here, they should have a destructive interference. That's how they designed the instrument. Good. So if there is any change in length or breadth of the device, what will happen? There will be change in the interference pattern, correct? Because the waves will not cancel out each other perfectly, because it's laser. It's not a visible. It's not a normal tube light or anything. It's a laser light which is extremely precise, extremely coherent and intense. Which means even if there is a small change in length and breadth of the device, what will happen? The interference will not be destructive, and there will be some amount of light that is distorted. That will be detected by a photo detector here. And now the second question is, will there be change in 4 kilometer because of smaller gravitational waves that is being emitted from the binary neutron system, which is located few million light years away? So to do this, what we do is, we subject it to multiple reflections. So 4 kilometers into 300 times reflection. So what will happen? Basically, the light will travel 1200 kilometers. That is the principle. So they designed it using a cavity called as Ferrot cavity. That's given in the diagram. So that Ferrot cavity, it is designed in such a way, each of the laser beam, it will travel front and back and forth for 300 times, which means each of the beam will travel to 1200 kilometers before meeting for an interference. So now, if there is even a small amount of change in length or breadth of one of the arms, what will happen is, one of the wave will be distorted. So using this distortion, we'll be reading that gravitational waves has hit the instrument. That is the overall principle on how LIGO works. Laser Interferometer Gravitational Observatory. And understand, LIGO is not the only gravitational observatory. We have one in European Union called as Virgo, and we have one coming up in India called as LIGO India. LIGO is in USA, and we have one LIGO that's coming up in India. Then Virgo is there in European Union. There is one gravitational observatory in Japan also. Good. Now you can write notes. You can draw a rough diagram. It's called as Fabry-Perot cavity. Fabry-Perot, not Ferrot. It's called as Fabry-Perot cavity. Important. Basically for amplifying the distance. We are using a 4 kilometer tunnel, and we are making the light to travel for 1200 kilometers. So a beam splitter will be splitting the light and sending it to two different cavities. Just play a video. Screen sharing pottingla.
At about 6 o'clock in the morning on September 14th, 2015, scientists witnessed something no human had ever seen. 2 black holes colliding. Both about 30 times as massive as our sun, they had been orbiting each other for millions of years. As they got closer together, they circled each other faster and faster. Finally, they collided and merged into a single, even bigger black hole. A fraction of a second before their crash, they sent a vibration across the universe at the speed of light. And on Earth, billions of years later, a detector called the Laser Interferometer Gravitational Wave Observatory, or LIGO for short, picked it up. The signal only lasted a fifth of a second and was the detector's first observation of gravitational waves. What are these ripples in space? The answer starts with gravity, the force that pulls any 2 objects together. That's the case for everything in the observable universe. You're pulling on the Earth, the Moon, the Sun, and every single star, and they're pulling on you. The more mass something has, the stronger its gravitational pull. The farther away the object, the lower its pull. If every mass has an effect on every other mass in the universe, no matter how small, then changes in gravity can tell us about what those objects are doing. Fluctuations in the gravity coming from the universe are called gravitational waves. Gravitational waves move out from what caused them like ripples on a pond, getting smaller as they travel farther from their center. But what are they ripples on? When Einstein devised his theory of relativity, he imagined gravity as a curve in a surface called space-time. A mass in space creates a depression in space-time, and a ball rolling across a depression will curve like it's being attracted to the other mass. The bigger the mass, the deeper the depression, and the stronger the gravity. When the mass making the depression moves, that sends out ripples in space-time. These are gravitational waves. What would a gravitational wave feel like? If our bodies were sensitive enough to detect them, we'd feel like we were being stretched sideways while being compressed vertically, and in the next instant, stretched up and down while being compressed horizontally. Sideways, then up and down. This back and forth would happen over and over as the gravitational wave passed right through you. But this happens on such a minute scale that we can't feel any of it. So we've built detectors that can feel it for us. That's what the LIGO detectors do. And they're not the only ones. There are gravitational wave detectors spread across the world. These L-shaped instruments have long arms whose exact length is measured with lasers. If the length changes, it could be because gravitational waves are stretching and compressing the arms. Once the detectors feel a gravitational wave, scientists can extract information about the wave's source. In a way, detectors like LIGO are big gravitational wave radios. Radio waves are traveling all around you, but you can't feel them or hear the music they carry. It takes the right kind of detector to extract the music. LIGO detects a gravitational wave signal, which scientists then study for data about the object that generated it. They can derive information like its mass and the shape of its orbit. We can also hear gravitational waves by playing their signals through speakers, just like the music a radio extracts from radio waves. So those 2 black holes colliding sounds like this. Scientists call this slide whistle-like noise a chirp, and it's the signature of any 2 objects orbiting into each other. The black hole collision was just one example of what gravitational waves can tell us. Other high-energy astronomical events will leave gravitational echoes too. The collapse of a star before it explodes in a supernova, or very dense neutron stars colliding. Every time we create a new tool to look at space, we discover something we didn't expect. Something that might revolutionize our understanding of the universe. LIGO's no different. In the short time it's been on, LIGO's already revealed surprises, like that black holes collide more often than we ever expected. It's impossible to say, but exciting to imagine what revelations may now be propagating across space towards our tiny blue planet and its new way of perceiving the universe. If you enjoyed this lesson, we think you'll enjoy reading or listening to Astrophysics for People in a Hurry by Neil deGrasse Tyson. You can find a link to the book in the description below. And if you love our channel, please consider supporting our nonprofit mission on patreon.com/TEDEd. Thanks for watching.
All right, so that's a basic principle. If there's a question or a statement saying gravitational waves can stretch and squish you, the answer is yes. But it happens on a very minute scale that we cannot feel it. Good. So it stretches in one direction and compresses in other direction. We call it as differential arm or differential displacement. Remember the terms stretch and compress. So basically one side it stretches, the other side it compresses. Coming to the next one. So it's yet another video. You can just watch it once and then go to the next one. So we have a beam splitter, and then it splits, and then it's reflected for around 300 times. And when it reaches back, if the arm length is exactly same, it should cancel out each other. Basically, we should have destructive interference. And if there is a change in the length,
distort space.
there is
and
one
changes
thing
the
that is
distance
stretched.
between the
This
mirrors.
is an exaggerated
One arm becomes a little
scale,
longer,
but still,
the other a little
there
shorter.
is any
An
stretching
instant later, they switch. This back
or
and forth stretching and squeezing
compression.
happens over and over until the
Stretching or
wave is
compression.
passed.
Either way,
As the distances
the
change,
interference pattern will
so
change.
does the alignment between the peaks
So
and
that will be
valleys of the two
detected by the
returning light
photodetector.
waves.
This is
And
the
light
overall idea.
waves no
Yeah.
longer cancel each
Coming to
other
the next
out
one.
when added together in the recombined beam. Now some light does reach the detector with an intensity that varies as the distance between the mirrors varies. Measure that intensity, and you're measuring gravity waves.
The light takes longer time in here than it did in this arm. Now it takes a shorter time, and these things don't cancel so beautifully anymore.
All right. So we have two LIGO observatories in US, separated by somewhere 3,000 kilometers. So that the main idea or main reason for keeping multiple observatories is to avoid noise. Imagine we capture a wave, and we have to cross-check it with the other places also, other locations also. We have two LIGO observatories in USA, and which is built by Caltech. So along with that, we have one in India that's being constructed. So these are some of the observatories for gravitational waves. LIGO, one in Hanford and Livingston. Virgo is from Europe. GEO 600 is in Germany. And Kamioka Gravitational Wave Observatory or detector is in Japan. Good, done. Could you please show the previous slide ones? This one. Sri Lakshmi, done. We'll go to the next one. Can we? Okay. So coming to LIGO India, it's important. Okay. My first question. So LIGO project in India, So ISRO will participate in LIGO India project. True or false? Make a random guess. Okay. Any answer here? LIGO India. Along with Caltech, ISRO will also participate in LIGO India. Okay. Second question. Along with Caltech, Indian Institute of Astrophysics will participate in LIGO India project. True or false? Okay. So Caltech plus Indian Institute of Astrophysics. True. Okay. So because when we think about gravitational waves and all astrophysics event, we'll be thinking about Indian Institute of Astrophysics or Indian Institute of Science, IAS in Bangalore, and then ISRO. But all these three are not participants in LIGO. So basically, we have Raja Ramana Center for Advanced Technology, then we have Institute for Plasma Research, and IUCAA in Pune. So the organizations which I told you, Indian Institute of Astrophysics or Indian Institute of Science, they may be playing an indirect role, but directly Caltech is coordinating with these three centers. RRCAT in Indore, one in Ahmedabad, and other in Pune. So if you get a statement saying ISRO is a part or IAA is a part, we'll easily tick the answer is correct. But understand, no, they're not part of it. So LIGO India will be set up somewhere near Hingoli district in Maharashtra. The most recent update is the instruments are going to be indigenously produced in India. Expected to be launched in 2025. We have around 4 more years to go. Land acquisition part is over. The instrument manufacturing process is ongoing. It's all going to be indigenous manufacturing. We are not going to import instruments. Most of the instruments, they are going to be indigenous. This thing also you can add to the Atmanirbhar Bharat points.
It's like public-private relationship.
Yeah, it's a public-private partnership, but all these are government institutes. So effectively for the partnership, we are going to manufacture instrument rather than importing it, which means the manufacturing capability of India is increasing. You can use it that way. Good. We'll go to the next one. Next, we are going to talk about IAO, that is Indian Astronomical Observatory, that is situated in Mount Saraswati. So IAO, Indian Astronomical Observatory, it's a collection of 4 satellites, which all are ground-based. We have 4 telescopes. We have 4 ground-based telescopes, of which 3 are right now functional and 1 is being constructed. It was supposed to be launched in 2021, but because of the pandemic, it's hit. We can expect a year delay. So it's located in Hanle in Leh, Ladakh. Good. So IAO, it's in Hanle. Few important points about it. It's a high altitude station of Indian Institute of Astrophysics. It's located in Mount Saraswati. Formerly, it was called as Dikpa Ratsari. This is the old name. The mount has been renamed as Mount Saraswati. It's located in Hanle, which is a village in Ladakh. We have 4 telescopes. Coming to the next one. These are the 4 telescopes. Growth India, Coming to the next one, first one, Growth India. It's important because Growth India was the first robotic telescope of India. Only maintenance is being carried out there, where in the day-to-day operations, it's coordinated from Hoskote in Bangalore. So basically, Indian Institute of Astrophysics, IIA, they have a facility near Bangalore that will operate and receive data from the Growth telescope. So the first robotic telescope, and it is observing transient events. Important word is transient. Don't confuse it with the TESS, which is transiting. This is transient. Transient means an event occurring for a much smaller time. So transit photometry is related to dip in the brightness of light. That is transit. This is transient. Basically, events occurring for a smaller amount of time. Global relay of observatories watching transients happen. It's a network of telescopes, and Growth India is one of the telescopes. So basically, it can observe in infrared plus visible spectrum. It can observe events in infrared as well as visible spectrum. Important. Considered to be optical telescope, but it can observe partially in infrared also. Three important things related to Growth telescope. First thing, whenever the LIGO apparatus, whenever the LIGO experiment, it is detecting a binary merger, binary neutron or binary black hole or neutron binary merger. So the same explosion event, it will be tracked by the Growth telescope. That's the first thing. Second thing, whenever there is supernova explosion, I told you it emits gravitational waves. So those events will be tracked in optical spectrum by Growth. And third one is it will be studying about asteroids. One peculiar point about Growth India telescope, it is studying about asteroids also, especially the near-Earth asteroids. They are also considered to be transient, which means asteroid crosses in a short amount of time. So it will be crossing the Earth in a short amount of time. If you want to read about asteroid, when it's crossing the Earth's surface, you have to make quick reading about it. So for this reason, we are using the transient telescope for reading. First thing, black hole merger. Second thing, supernova explosion. Both the things are related to gravitational waves. And third thing, we'll be using it for studying asteroids also, which are transient in terms of time. After Growth, it's Himalayan Chandra telescope. So which is optical to infrared again. So optical plus infrared. And this is the highest observatory for optical and infrared astronomy. Important. Done. And coming to the next one, HAGAR, that is high energy gamma ray telescope. The name itself says it's going to read about gamma rays. It will be reading about the Cherenkov radiation. Did you ever come across this term called as Cherenkov radiation? If you people have watched the series called as Chernobyl, you would have come across this thing called as Cherenkov. Anyone online? What is Cherenkov radiation? Any random idea? Make an attempt, right or wrong, it's fine. Participating is important. Can someone tell me what is meant by Cherenkov radiation, or what possibly is Cherenkov radiation? People? Cherenkov radiation. Okay, I'll tell you. So what is the speed of light in vacuum? It's called as 3 into 10 power 8 meter per second. We know 3 into 10 power 8 meter per second, one of the highest velocity we ever know about electromagnetic wave. Good. So this is the speed of light in vacuum, not in air or not in water. But when light travels in water, it travels at somewhere around 2.25 into 10 power 8 meter per second, which is around 70% of its speed in vacuum. Good. So Cherenkov radiation happens when there is a particle that is traveling faster than light in that medium. So imagine in water, if any particle is going to travel much faster than the light, then it means it will cause a large amount of vibration and it will appear like a bluish glow. Whenever you search for pictures related to nuclear reactors, you could see a bluish glow, a light or bluish glow. It's because of Cherenkov radiation. It's named behind the scientist from Russia who discovered this radiation. So basically, Cherenkov radiation means if a particle is going to travel at a speed, travel at a velocity greater than light's velocity in that particular medium. It could be water, it could be metal or anything. So any element or any radiation, it should travel faster than light in that particular medium. So when it's going to travel faster than light at the particular medium, it will emit bluish glow that is called as Cherenkov radiation. So now, why is that this is reading high energy gamma rays, and what is it related to Cherenkov radiation? See, Earth has Cherenkov radiation in different scale in atmosphere. So imagine we have a mountain, and then we have the atmosphere here, that is end of atmosphere. Good. So if you want to read about gamma rays, I told you terrestrial gamma ray flashes. If you want to read about gamma rays, or if you want to read about Cherenkov radiation, there are two methods. First thing, you should build a telescope which is extremely precise, very large in size, and then you can place it in a plain area like Chennai or somewhere. You need to build a telescope that is extremely precise, which means it should neglect all other surrounding noise and everything, and it should read only the Cherenkov radiation and gamma ray flashes. This is going to be extremely difficult, both in terms of technology as well as cost. The second thing is, you can have a telescope that could normally detect gamma rays and that could normally detect Cherenkov radiation, but you have to place it in extreme high altitude where there is lesser atmospheric disturbances. So the second choice is placing it at a high altitude where there is lesser disturbances. So for this reason, Hanley is chosen. So Hanley is considered, since the highest point on Earth is 8848 meter, which is Mount Everest, but it's extremely difficult to construct a telescope here. We are placing it in Hanley, somewhere close to 4,000 plus meters above the sea level. For this reason, we are placing Hager here, basically for reading Cherenkov radiation and gamma rays. So it's actually 7 telescopes. This is one set. There is one more set here. There is one more set here. You could see basically 7 telescopes. A total of 49 receivers. 7 of them bundled in single unit, and there will be 7 telescopes here for reading Cherenkov radiation. So if you read very high energy gamma rays and Cherenkov radiation, we'll be able to detect the merger of pulsars, supernova remnants, microquasars, and active galactic nuclei. We read about all these terms. So gamma rays emitted from all these events. We're going to use this for reading about astronomical events. That's the overall idea. I'll be sending it to you through the notes. No need of writing the entire thing. Write down just basics like AGN, pulsars, etc. emit very high energy gamma rays, VHE gamma rays. So this is detected using Hager telescope. Coming to the next one. Basic definition for Cherenkov radiation: it is a type of light or a bluish glow light that's produced when a particle travels faster than the speed of light in that medium. So this is especially possible when nuclear fission or fusion happens. Whenever there is an atomic level explosion or when there is an atomic level event, then it will speed up particles. Imagine uranium breaking down into barium and krypton and emitting a lot of neutron. It's going to be emitted at a much higher energy, so neutrons possibly can travel at a speed faster than the speed of light in that medium. So in those cases, Cherenkov radiation will be produced, which is a form of gamma ray. On the latest one being constructed, it's called as MACE. I told about this, no problem, don't write it down. We need a large telescope at the plane, or we need a small telescope at high altitude. So this is in the method we are using. Next one, Major Atmospheric Cherenkov Experiment Telescope, MACE. It is again going to detect gamma rays and Cherenkov radiation. So this is the world's second largest gamma ray telescope. The first one is located in Namibia. This is going to be the second largest gamma ray telescope. Close to 1,000 mirrors, all being manufactured in India again. We are indigenously building a gamma ray telescope. We are not coordinating, or this is not a partnership with some other space agencies. This is solely built by India. So Baba Atomic Research Center plus Tata Institute of Fundamental Research plus Indian Institute of Astrophysics. All the private and public premier institutions, they are coordinating and they are constructing this indigenous technology. It's in Namibia. The first largest telescope is located in Namibia. It's called as you can search if you want. It's called as high energy stereoscopic system, I guess. I'm not sure. You can check once. It's called as HESS Namibia, high energy stereoscopic or stereotropic. I'm not sure. Check it once. HESS in Namibia, that's the largest one. Okay, coming to the next one, the only space-based observatory of India. No need of writing this. All the components are developed in India. This is important. Again, Atmanirbhar Bharat. And we have around 1,000 plus cameras and 300 plus mirrors. All together, it's going to form the MACE telescope. Coming to the next one, the AstroSat series. Before you start the AstroSat series, remember, this is a bit older. It was there in prelims question in 2015, I guess. It's a 2,000 kilogram single satellite that houses multiple telescopes. Basically, it has 5 payloads, and it can read infrared, visible, ultraviolet, and X-ray. Can read only these 4 electromagnetic spectrum. Good. Going to the next one. X-ray, optical, UV. I think infrared is not there, sorry. Only these 3, visible, UV, and X-ray. Can read electromagnetic spectrums in visible, UV, and X-ray. All the events related to visible light, about ultraviolet rays and X-rays can be studied using AstroSat. The main reason for studying multiple wavelengths of electromagnetic spectrum is, you can see this. I'll send you through the notes. All the cold gases, it will be emitting radio waves, and all the low temperature events, it will be in infrared. And stars that are presently live, it will be invisible. And ultraviolet will be emitted by white dwarfs. And all the hot gases or white dwarfs, they'll emit X-rays. So extremely high temperature events in X-ray. Other events in UV, normal events in visible, low temperature events in infrared, and all cold events in radio. This is the idea. So we are going to make simultaneous observation using single satellite. And objective, don't write it, you can read it once. We're going to read about the binary star systems, neutron stars, black holes. I've explained about all these to you, what is meant by neutron star, black holes, and everything. And second thing, we'll be estimating magnetic field of neutron stars. When you read this line, you have to remember about magnetars also. We have 10 magnetars, so we can use AstroSat to read about magnetars and other neutron stars. So the study of birth regions where protostars and everything forms. When protostars or when main sequence star forms, it will be emitting infrared rays, initially when they have lesser temperature. And then X-ray sources, which could be from high energy events like merging of black hole or accreting disk, everything, it will emit X-rays. So we'll be reading that also. And also it will be doing deep field survey in UV region, ultraviolet rays, which will be emitted by white dwarfs and everything. Good. So the most recent update is in 2016, it observed ultraviolet ray, which was up to 10 nanometer. High energy ultraviolet wave was observed by AstroSat. And recently they confirmed it's from a galaxy. So that's the most recent update. And main reason for having multi-wavelength observatories, we can read only radio waves from the ground. I told you earlier. Wherein most of the infrared spectrum, it's absorbed by gases. Visible light is also scattered in the atmosphere. Gamma ray, everything is absorbed by ozone and everything. So basically, we can read only radio waves from ground-based telescopes. The rest of them, it won't be precise or it won't be accurate. This is the main reason for having space-based observatory, which is going to be second space-based observatory. Any idea after AstroSat? The next space-based observatory will be Aditya L1, because it's going to observe sun and other events. So only interplanetary mission which we have succeeded is the Mars orbiter mission, which is outside the Earth, which is orbiting the planet Mars. Other than that, the most recent one is probably Aditya L1. We have planned to place it in L1. That will be outside the Earth's atmosphere, and it will be observing the sun. That will be one of the, it's not an interplanetary mission, but it's an observatory mission because it's going to observe the sun. Right now, we have only one space-based observatory, that's AstroSat. About payloads, don't write everything. Of the 5 payloads, UV-80 was in news in the last 2 years. Ultraviolet Imaging Telescope. This is the payload that confirmed the galaxy, AUD. AUDFS D1, that's the name. No problem, you can write this one. Hold on. Yes, it detected an extreme ultraviolet ray from a galaxy. It's called as AUDF S01. This is important because this is one of the rare discoveries that was made by an Indian astrophysicist using AstroSat. Don't write the entire thing. You can write the first one alone. Good, we'll go to the next one. Answer for this one, old UPSC question. Recently, they have observed merger of 2 giant black holes, billions of light years away from the Earth. What is the significance of this observation? Easy question. Yeah, people online watching the messages, can someone answer this? Okay, gravitational waves were detected. Yes. The most common mistake made by people when they wrote this exam was many people wrote this one. It enables scientists to understand singularity. No, till date, we have not understood what is meant by singularity. The answer is this. Good. Coming to the next one, a 4-decade-old mission. So I think with this, the astrophysics part is over. I have few space missions which I left out. But I felt it's necessary to cover, like GeoTail and X57 Maxwell. There are 1 or 3 trivial topics. We'll complete it and then go to the next one. We'll start with the nuclear science after this. First one, the longest living spacecraft by human, which is built by human. It's a 4-decade-old. It's called as Voyager. So Voyager 1 and Voyager 2. Basically, 2 spacecrafts that were launched in 1977. They crossed the solar system and they have entered the heliosheath, basically outside the sun's influence. Good. The farthest and the longest living spacecraft ever built by human, Voyager 1 and Voyager 2. It's a program by NASA. It has 2 Voyager 1 and Voyager 2. Write only the first 2 points. Don't write this. It's a program by NASA. Yeah. So the present position of both Voyager 1 and Voyager 2, both of them, they had a different path. So Voyager 2 was launched first and then Voyager 1. If you see, it was going through different planets. Jupiter, Saturn, Uranus, and Neptune. So basically Voyager 4, it has made closer flyby to all the 4 Jovian planets, wherein Voyager 1, it's right now outside the solar system. It crossed the Kuiper belt. This is important. Right now, they are interstellar medium, which means outside the bubble or outside the influence of sun. These years are not important. This is for your basic understanding. 2012, Voyager 1 crossed, and after 7 years, Voyager 2 crossed. The main reason for this much time gap is this. They followed different path. Right now, they are in interstellar medium. So now I have a doubt. So we cannot visually see if the Voyager is inside the solar system or if it's outside the solar system. So we basically determine if it's inside the solar system or if it's outside the solar system based on the plasma density. So what is plasma? I told you in the beginning of the class when we were discussing about sun. So basically plasma is emitted by all the stars. It's basically nucleus and electrons separated from each other. That's called as plasma. Now my question is, imagine this is solar system. The sun is here. After solar system, there is this magno-heliosheath where sun's influence ends. And outside this, it's all interstellar space. Space number 2, space number 1, that is inside sun's influence. My question is, how is plasma density in 1? Is it less dense or is it more dense? Compared to the second space that is outside the heliosheath, how is the plasma density in the space number 1, that is inside the sun's influence? Will the plasma be more dense or will it be less dense? Yes, both crossed heliosphere. Basically, they are in heliosheath right now. Basically, the border between intergalactic space and solar system space. The question is, how will be the plasma density inside the sun's influence or inside the heliosphere? Will it be dense or will it be less dense? Plasma density inside the heliosphere. More dense in one, high dense, more dense, okay. The density of plasma in one. Okay. Most of you say it's more dense, okay. So understand, you have a gas, you have a mass of gas inside the balloon. So once you start heating this gas, what will happen is it will expand. So when it expands, what will happen to the density? The density will drop. So similarly, inside the heliosphere, inside the influence of sun, the plasma density is low. And temperature is high. So once it crosses the heliosphere, what will happen is it will face a region where the temperature is low and the plasma density is high. So if Voyager is detecting that the plasma density is increasing, it means it's exiting the solar influence. That's how we mark the solar exit, the region where plasma density becomes higher and temperature becomes cooler. So heliosphere has less density of plasma. If you want to write it in technical term, you can write this: hot and low density plasma to cool and higher density plasma. That marks the solar exit. How plasma density is low? Okay, as now imagine I have a helium gas, which is much lighter. You know, helium balloons that can easily fly. They are much lighter. Good. So I'm going to heat this helium because I'm placing it close to a flame. Placing the balloon close to a flame, I couldn't draw the really neat flame, understand? So this flame starts heating up the balloon. What will happen to the helium gases? They'll go far away from each other. So effectively, the space will increase. The same amount of helium will be present at a much, separated by a much longer distance, which means the temperature will be higher, but the density will be lower. Am I right? Archana, do you get it now? Basically, you have a gas which is closed in it. Yeah. So imagine replace this flame by sun. So what will happen? The galaxy, every gas present in the galaxy starts expanding. The plasma also starts expanding, which means the amount of plasma is distributed in a larger space, which means the temperature will be low and density also will be low. Sorry, the temperature will be high and the density will also be low. Heating it, density is lower, temperature is higher because it's closer to a flame. So temperature increases, density decreases. Clear? Done. Coming to the next one. Most important thing, see, the place where the solar radiation starts interacting with the interstellar radiation, the place where the radiation mixes, it's called as terminal shock. The inner side of helio sheath is called as terminal shock. So after terminal shock, the point of interaction or the exit, it's called as helio sheath. Once the helio sheath is over, you have heliopause. Heliopause, as the name says, it's a pause, it's a stop. So basically the solar radiation is completely cut off here. The magnetic influence of sun, it's completely cut down here. That's why it's called as heliopause. So heliopause, the central part is helio sheath, the inner part is terminal shock. A more technical definition is here, you can write it. You can draw a rough diagram. Followed by that, we have definition in the next slide. So the entire boundary of solar influence, it's called as heliosphere. The place where heliosphere starts interacting with the interstellar medium, that's called as heliosheath. The inner part of heliosheath is terminal shock, the outer part is heliopause. Heliosheath is divided into two. Right now, Voyager 1 and 2 are in heliosheath, somewhere in heliosheath. They have not crossed the heliopause. They have not entered the intergalactic medium. Done. We go to the next one. One important discovery about Voyager 1 and 2. Can someone say which is the largest moon in the solar system? The largest moon. I told you earlier when we were discussing different planets. Can someone say the largest moon in the solar system? Shivapriya says Titan. Any other answers? The largest moon in the solar system. Screen sharing off and Leo. இவ்வளோ நேரம் நான் தெரியல போல இருக்கு. Is it Titan or is it Ganymede? So yeah, it's actually Ganymede. I told you Titan was in news for the past 2 years because of discovery of methane lakes and everything. But actually, Ganymede is the largest moon in the solar system, which belongs to Jupiter. Saturn is the second largest moon and belongs, Titan is the second largest moon and belongs to Saturn. First is Ganymede. Second is Titan. Ganymede belongs to Jupiter and Titan belongs to Saturn. Two important moons to remember. Along with it, remember Triton. Not Titan, it's Triton. T-R-I-T-O-N, Triton. So Triton is a moon that belongs to Neptune. It's a natural satellite of Neptune. It's special because it's the only moon that orbits in opposite direction compared to the planet's rotation. I repeat, see, we have Earth. The Earth is spinning from west to east in this direction. So how is the moon orbiting around us? It's orbiting in the same direction. So almost all the natural satellites, they orbit in the same direction as the planet's rotation. But wherein Triton, the Neptune's moon, it is rotating in opposite direction compared to the rotation of Neptune. So this was discovered by Voyager 2 because Voyager 2 is the only man-made spacecraft that has visited all the Jovian planets or all the gaseous planets, the planets outside Mars. Jupiter, Saturn, Uranus, and Neptune. All the 4 planets were visited by Voyager 2, and it made this discovery that Triton is orbiting in opposite direction. It's the coldest known object in the solar system, even outside Neptune, close to the Kuiper belt. Coming to the next one, in last 1.5 years, these two things were in use related to Voyager. I'll tell you why. First one, DSS-43 antenna. This is located in Australia. So this was scheduled for maintenance because for the past 40 years, we were using this DSS-43 antenna for communicating with Voyager. But, so DSS-43 antenna, it was set for upgradation. So right when the upgrading thing was happening, the COVID pandemic hit. So because of that, the entire project was stalled, and we cannot communicate with Voyager for a very long time. So all these spacecraft, it's equipped with something called as command loss timer. So command loss timer, it is to avoid electronic slumber. So what will happen is, if the Voyager did not receive signal from us for a very long time, so it will understand that because of some technical issues, it's not receiving the signal. So it will shut off the reception, signal receiving part, and it will operate only the transmitting part, which means the two-way communication will become a single-way communication. So it will protect itself. Instead of receiving command from us, it will put it in an automated mode, and it will keep on sending data to us. So instead of a two-way communication, it will become a single-way communication. We will receive data from Voyager, but we cannot communicate with Voyager. To avoid this electronic slumber, for the first time, we used very small antennas to transmit small amount of data to Voyager. So understand, it's possible to communicate with Voyager using a small antenna. Good. Right now, DSS-43 is upgraded. Right now, currently operational. Voyager is not into electronic slumber. This term is important. Command loss timer, generally equipped in almost all the long-distance spacecrafts. So if there is no signal, operation will be automated. Two-way communication will become one-way communication. The spacecraft will broadcast data wherein it will not receive signal from us. That is the overall idea behind command loss timer. Coming to a few of the important first one, Voyager 1 was the first spacecraft to enter or cross the heliosphere. Second one, it's the first man-made object to venture into interstellar space. Also understand the list of man-made objects that has ever crossed the heliosphere. It's not just Voyager 1 and 2. Other than that, we have New Horizons spacecraft. You can write it on the right side of the page, just like a small additional box. New Horizons spacecraft. This has crossed the Kuiper Belt. And then we have Pioneer 10 and Pioneer 11. But these two are not in news for the past 4 or 5 years, mainly because we lost connection with it. So right now they're traveling outside the solar system, but we don't know their present location. They have lost contact with the ground center, which means they're still traveling, but it's not active mission. It's a defunctional mission. So we have to read about Voyager 1, 2, and New Horizon, and lesser about Pioneer 10 and 11. Coming to Voyager 2, it's important because, as I told you, it's the first spacecraft that was able to study about 4 Jovian planets or gaseous planets. The only spacecraft that has studied all the 4 planets. First spacecraft to visit last 2 planets of the solar system. So if you get any questions related to Uranus and Neptune, you can relate it with Voyager 2. Wherein if you get any questions related to Kuiper Belt objects, called as KBO, any questions related to Kuiper Belt objects, you can relate it with New Horizon spacecraft, because that is extensively reading about the Kuiper Belt objects. Then we'll go to the next one. Next is New Horizon spacecraft. So mainly it is studying about Pluto, and it is reading about Kuiper Belt objects. New Horizon spacecraft by NASA. Done. So the most notable discovery, did someone come across this term called as Charon? So we shrunk the solar system, we neglected Pluto outside, we call it as dwarf planet. And this dwarf planet has a moon called as Charon. This was discovered by this New Horizons spacecraft. So notable objects studied are Pluto and Charon. And another most notable discovery is it's called as Ultima Thule. Ultima Thule. It's pronounced as Tooleh, Thule. So it's a trans-Neptunian object which is in the Kuiper belt. It used to be called as the space snowman because it looks like a snowman, but it's no more called as snowman because it appears to be reddish in color. It's not white in color. It's a Kuiper belt object. KBO, generally called as Kuiper belt object. Any object present in Kuiper belt that is outside Neptune, where Pluto is present, we call it as a Kuiper belt object. The peculiarity is this is not an asteroid, this is not a comet, this is unknown type of object. So which is in a pristine and primordial condition. We are going to send more mission to read about it. And now recently they have renamed it. So Ultima Thule, the name, it has some Nazi connection. So it sparked a huge row. It's following that they renamed it as Aroko. Again, a Hawaiian language. So officially it was called as MU69. When we were reading about SOFIA, we told you it helped in detecting MU69. MU69 is the official name of Aroko or Ultima Thule. So Voyager 2, it is coordinating with SOFIA also. That's why I told you SOFIA, it is repeatedly in news. Like it is assisting other important missions. So it has been renamed as Aroko. It's a Algonquian language, which is spoken by the people in Powhatan tribe. They are in Maryland in USA. Maryland is here. So local tribal group. They're called as Powhatan tribal group. The language is Algonquian language. And in that, it has been named as Aroko, which means sky. They even call the tribal leader for naming ceremony and everything. This was in news again. We have a small referendum now. So I thought I would personalize the biology topic. So after this, we have to deal about the people online. You have to participate because I have lesser people here in offline mode. So depending on your message replies, I have to decide. So there are two choices. The first choice is I'll take one more class. That is in the next week. I'll just give you the recent developments in biotechnology and then wind up the class. That is in 8 classes. Or choice number 2 is I'll take 2 classes. The first class, I'll give you a basic idea about static biology because most of us are from engineering background, very few people from biology background. So most of us from arts and science and commerce background or from engineering background. So what I'll do is one class I'll take for giving you idea about static biology portion, which will include all the respiratory system, circulatory system, nervous system and everything. And in one more class, I'll be completing the recent developments in biotechnology. So which one is preferred? Is it static plus current affairs? Or is it enough if I cover the current affairs? 2 classes? Yeah, static plus current affairs. Depending on your answer, I have to ask for the classes here. Okay. 1, 2, 3, 4, 5. Okay. So in that case, so the next class will cover nuclear technology and then statics of biology. And in the next class, I'll give you a basic introduction about recent developments in biotechnology and everything, and then we'll wind up. Good. Okay. Coming to the next part, an important one that's called as magnetospheric multiscale mission. You could see 4 spacecrafts. Magnetospheric multiscale mission. So the basic principle is, see, we have sun. Sun is emitting a large amount of magnetic field. And then we have Earth. Earth also has a magnetic field. So at some point, these two magnetic fields will interact, correct? So the magnetic field of sun and the magnetic field of Earth will interact. So at the point of interaction, they'll be accelerating the particles close to speed of light. Close to speed of light, they'll be exciting and accelerating the particles. So this phenomenon is called as magnetic reconnection. So where reconnection happens between two different magnetic fields. And this also happens on rear side of the Earth, where two different magnetic fields they'll meet. And whenever there is magnetic reconnection here, again, particles will be accelerated. So this event is being studied by a mission by NASA called as MMA, Magnetospheric Multiscale Spacecraft. You have to write this one. It's a 4 spacecraft flying in the formation of a pyramid. So whenever magnetic reconnection happens, there is a giant explosion of energy and particles will be accelerated. Any particle, protons, neutrons, and every particle, it will be accelerated. So this is considered to be the main reason for triggering auroras, what we call as aurora borealis and australis, the northern lights and southern lights. They're mainly caused because of the magnetic reconnection. 2 types of magnetic reconnection, one that happens in the front part of the Earth, that is the sun facing side, the other one that faces far side. You could see this is how magnetic reconnection works. So basically the magnetic fields interact and they reconnect. So we are reading this using magnetospheric multiscale mission, basically studying about reconnection. Second important thing is this magnetic reconnection, this is not specific only to the Earth, it happens throughout the universe. Even on the sun, recently we predicted this magnetic reconnection, it can cause coronal mass ejections. Take a look at the simulated video. So when there is magnetic reconnection on the surface of Earth, on the surface of sun, it could actually trigger coronal mass ejections, which means high amount of charged particles, gravitational field, magnetic field, and plasma being ejected from the surface of sun, which affects the GPS system and everything. So coronal mass ejections can be triggered by magnetic reconnection. Magnetic reconnection is not specific to sun and Earth alone, it appears throughout the universe. That's important. It's a fundamental process. Basically, it's converted into heat and energy. So Archana is asking how this happens in other parts of the Earth. You understand? Imagine Earth is like this. I'm not considering the tilt. If you take this, if the magnetic field wants to enter in perpendicular direction, then it has to cross all these lines of force. It's difficult to come inside, so it will be deflected. Wherein something has to enter in this direction, it's easier, correct? Because it's traveling along the line, magnetic lines of force. So that's why we have these auroras only in northern and southern hemisphere, not anywhere closer to the equator or anything. So basically, the magnetic field, it can travel easier inside. Similarly, cosmic rays also. We have more cosmic rays in poles than in equator and other parts. So this happens only in poles and a negligible amount in other parts of the Earth. That's not clear? Yeah. So when the charged particles enters the top and bottom part, it triggers auroras. Colorful events in northern hemisphere and southern hemisphere. So don't write the entire thing, you can write this alone. Done. Go to the next one. So next we have geotail. Does someone remember which one has the payload called as TMC, Terrain Mapping Camera? TMC, Terrain Mapping Camera. It was a payload of one of the India's missions. Terrain Mapping Camera. Netra, no, it was the part of Chandrayaan 1. Next, I told you there are two components. One is the Moon Impactor Probe. The other one is the orbiter. The orbiter has a payload called as Terrain Mapping Camera, TMC. Yeah, Archana. Coming to the next one, there is one more thing called as CLASS. This was in news recent. What is CLASS? Or which Indian mission has the payload called as CLASS? It's large area soft X-ray spectrometer. So Chandrayaan 2. It's in Chandrayaan 2. Yeah. Chandrayaan 2, large area soft X-ray spectrometer. So this was in news because recently it studied X-ray spectrum of particles on the moon using a phenomenon called as geotail. So this was in news recently, much recently, I think before 3 or 4 months. I'll tell you what I mean by a geotail first. See, I told you Earth has a magnetic, Sun has magnetic field, and then Earth has magnetic field. On both these magnetic fields, they interact at a point, and then it causes magnetic reconnection. So what will happen is, since Earth has a global magnetic field, it will try to obstruct the Sun's magnetic field. So at this point of obstruction, it will create an envelope, a much compressed area. Good. So at this envelope, magnetic field cannot enter. Good. So basically, this is extremely compressed since it's like two opposite poles facing each other. It will be extremely compressed. And this point is called as magnetosphere. When we're talking about heliosphere, I told you it is the field of influence of Sun's magnetic field. Here we are talking about magnetosphere, which is field of influence of Earth's magnetic field. So magnetosphere is created about troposphere, stratosphere, mesosphere, ionosphere, exosphere, and then you have magnetosphere. If you would have read in the environment also. Troposphere, stratosphere, mesosphere, ionosphere, exosphere, and the last we have magnetosphere. So basically it will be somewhere close to 3 times the radius of Earth. The thickness will be somewhere close to 3 times the radius of Earth. So the reason why we call it as geotail is the front part or the sun-facing part, the magnetosphere will be much compressed, where in the rear side, it will be stretched like a tail like this. So it will be much stretched, and the magnetic field is not strong at these points. So imagine the moon is here. What will happen is the solar radiation can reach these points. So at these points, the solar radiation, it can reach the sun. And when it reaches the sun, what will happen is there will be high amount of X-rays. When high amount of X-ray falls on the moon, what will happen is the elements present on the moon, it will absorb the X-ray and it will emit it back. So based on the emission spectrum of the particles present on moon, we can check if calcium is present, if iron is present, or what are the elements that are present on moon. So basically the overall idea is like this: extremely compressed magnetosphere. Here it is tail-like portion. So the X-ray part of solar radiation, it falls on the moon when it is on backside. When it is on backside of the geotail. So the moon surface receives X-ray. So when X-ray is received, it will be absorbed and then it will be re-emitted back. So this will be studied by a spectrum, by a payload called as CLASS. So once in a month, Moon will be 6 days in geotail. So CLASS instrument is utilizing these 6 days to study about the X-ray spectrum. This is the overall idea. Good. Technically, you can write down the definitions like this. The region as a result of interaction between Sun and the Earth. Magnetospheric multiscale mission is a much older one, which is currently active, but Geotail was there in news recently. So understand, Geotail and magnetospheric rescale mission, multiscale mission, both are related, closely related to magnetic reconnection, where particles will be accelerated close to the speed of light. Always remember. Coming to the next part. All you have to write in this is this one. So interaction between global magnetic field and the solar wind plasma, it results in a region called as magnetosphere. So magnetosphere is close to 3 to 4 times the radius of Earth. So for every 29 days, Moon will be in the geotail portion for 6 days, which means CLASS cannot study the X-ray every single day. When it's in geotail portion, it is studying. For one lunar cycle, it can stay in the geotail for 6 days. This is the overall idea. In this, you write about the payload alone. Chandrayaan-2 large area soft X-ray spectrometer. So it's detecting signature of elements on the moon soil. Basically, how it interacts with X-ray. Sorry. Sri Lakshmi, you can write it now. Clear? Can I change? Even before this, okay. Clear? Magnetosphere, it's basically magnetic envelope, 3 to 4 times the radius of Earth. It's a result of interaction between Earth's magnetic field and solar wind plasma. That's all. Done. Yes. Coming to the last one. No need of writing this. You can read it once. So basically, it's detecting the presence of key elements depending on the reflection of X-rays. Next one is X57 Maxwell. So X57 Maxwell is important because this is the first all-electric aeroplane, which is going to be introduced by NASA. So basically, it will have somewhere close to 14 electric motors, of which 2 will be larger in size and 12 of them will be smaller in size. So it's like small drops make a mighty ocean. It will be used for smaller thrust. So initially, takeoff thrust will be taken care of by the smaller motors and then the large motors. The main idea behind this is space taxi or air taxi. So it cannot be used for long distance communication. Understand? Right now, for the present capability, we cannot use it for a long distance flight. We can use it for a short distance flight, by which means NASA is planning to use it as air taxis. So it's called as X57 Maxwell. X57 is important because X means experimental. So basically, NASA has other experimental flights. One was the first experimental flight that crossed the sound barrier, which means it traveled faster than sound. What is the speed of sound? On an average, it's 343 meter per second. So anything that crosses this, we call it as a supersonic. More than transonic, we call it a supersonic. So anything that crosses the sound barrier is called a supersonic speed. The first supersonic speed was a experimental X series flight. It's called as Bell X1 and then X15. These two are important experimental flights of NASA. Bell X1 broke the sound barrier. X51 was flown by Neil Armstrong before he came into the moon mission. It's powered by lithium-ion batteries. No newer technology. Again, the old technology, lithium-ion batteries. It's going to be used as air taxi. X57, I'm not sure if it travels in supersonic speed. Oh, you're asking about X57? No. It will not travel in hypersonic speeds or anything. It's a low budget flight which will fly at a normal rate, not a supersonic speed or anything. It's not a super fast. Rather, it's opening a new chance for building air taxis for short distance commutes. Imagine a Ola, Uber like that, like company offering you air taxi. Done. So the last part, meteor shower. So So first question, what is the difference between a meteor and a comet? What is the difference between a meteor and a comet? So Arshia, I think we don't have Chandrayaan-2 payload slide right now. That was in second or third class, I guess. I don't have the slide with me right now. I'll send it in short notes. The lunar mission, we handled it much before 2 or 3 classes. I don't have the slides with me handy right now. Please remind me if you are not getting the short notes. Arshia, is it clear? Okay, comet has tail, meteors don't have tails. Okay. Meteor is from solar system, comet is from outside the solar system. Okay. Difference in the orbit. Okay. See, the basic principle is, first thing, we have sun and we have solar system that is extending up to Neptune. There are any rocky structures that is orbiting the sun. Between these orbits, you call it as asteroids. I told the term rocky, which means generally it does not have ice, it does not have any other thing, methane or anything. Generally it has just rock and metals. Good. Coming to comets, comet also orbits the sun, but they are from outside the solar system. They are not from the solar system. They are sometimes called as heavenly objects because they're not part of solar system. They come from outer space, generally from a place called as Oort cloud. OORT, Oort cloud. From this, they'll be approaching the sun, they'll be orbiting the sun, which means they'll make a highly eccentric orbit. Somewhere outside the solar system, they'll come closer to sun, and then they'll go out like this. So this is what comet does. Basically, asteroids, they are like planets, but they're not large enough to be planets. Wherein comets, they're totally different. They make an elliptical or a highly eccentric orbit, where sun is located at one of its foci, extreme end of its foci. And the main difference is, someone was telling comet has tails. Exactly. Why comet has tails means, imagine the comet has large amount of ice and methane. It has ice and methane. Imagine a comet is approaching sun. What will happen? When it comes closer to sun, the temperature will increase. What will happen when the temperature increases? Ice will melt, methane will burn. So because of that, it will create something like this, a tail like this. We were reading about the geotail. Similarly, comet will also create a tail. So that's why it has a tail-like appearance. Wherein, if you look at a comet like this, there will be a small central part that is rocky. That's called as nucleus of the comet. So generally, the comet is smaller, but the image it gives is larger because the methane and ice is melting and it's forming a huge trail. This is the overall idea. Good. So meteors or asteroids, they are inside the solar system, wherein comets are from outside the solar system. So meteors and meteorites, they have meteors, meteorites, and asteroids and everything. They have only metals and rocks, wherein comets has methane and ice structure. This is the main difference. Now coming to meteors and meteorites, first thing. So generally, when some part of asteroids or some part of comets, it is separated from them and then it enters into the Earth's atmosphere, we call it as meteoroid. The general term is meteoroid. There is a common misconception that meteor shower is related only to comets. Understand? Even asteroids cause meteor shower. Not only comets, even asteroids causes meteor shower. Good. So when some part of, say, some rocky layers or some small speck of asteroid or a comet, it is separated from them, and then Earth enters into that path, it's called as meteoroid. So meteoroid is divided into 2 parts. One is meteors, the other one is meteorite. So imagine this is Earth and we have atmosphere, and then a rock enters into the Earth's atmosphere. What will happen? There will be a huge increase in temperature because the air will create friction. The friction will create increase in temperature, and the rock will start burning. So if it burns out before it reaches the surface of Earth, you call it as meteor. It does not hit the surface of Earth. It's completely burnt out, and only ash. It turns into ash. It completely disintegrates. That is called as meteor. So if the meteoroid is large enough that even after burning, if it reaches the Earth's surface and makes a huge depression, you call it as meteorite. So meteorite basically reaches the surface of Earth. Meteors burns and disintegrates completely before it reaches the surface of Earth. Both of them collectively, they are called as meteorite. So meteorite can be from comet as well as from asteroid. This is the overall idea. Is it clear? So what does it mean by meteorite shower? On a regular interval, there will be an increased meteoritic activity. Meteorites will be increased. That's because Earth will be regularly crossing few points where high amount of dust is present. Imagine this is Earth's orbit. And there are points where there are high amount of dust created by asteroid and comets. So whenever Earth is crossing this region, it will have high meteors. When it's crossing this region, it will have high meteor. So these regions are called as meteoritic shower. So actually the meteors are not reaching us. We are traveling towards the meteor. That is called as meteor shower. Main difference between meteoroids, meteors, and meteorite. Even though we say that meteors enters Earth's atmosphere, Earth is actually traveling towards this meteor. So we didn't give a break. So I'll be completing in another 10 minutes. I think it's fine, no? We'll wind up somewhere close to 7:15 to 7:20. Done? As I told you, this is the comet's orbit and the Earth's orbit. So drastic increase in meteors is called as meteor shower. You don't have to write it, you can read it once. The Earth passes through the trails of dust. Dust doesn't reach us, we are traveling towards the trail of dust. Left by a comet and or asteroid. It's not just comet alone, it's caused by asteroid dust also. Now coming to different meteor showers, annual meteor showers. 4 meteor showers were there in news. We have many meteor showers, but 4 were in news. Don't write it. This is a snapshot from the notes which I'm preparing for you people. If you take a look at this, there are 2 meteor showers, that is Geminids and Quadrantids. These 2 are caused. Generally, remember year end, December and January. So the meteor shower caused the year end and the year beginning. The Quadrantids and Geminids, they are caused by asteroids. The rest of them are caused by comets. They occur annually. Clear? Okay. With this, the astrophysics, space science part is over. I have to start with nuclear science, and then biotech is left over. So I think if I start nuclear science now, I won't be able to complete even the basics. So we'll wind up here. Don't leave the meeting. Hold on. Since most of you people are fresh graduates, I'll give you one more mains answer writing today. So this is not going to be for 150 words. It's going to be for 250 words. 250 words and 15 marks. You don't have to send it to me. You can write it and keep it safe, because this is based on nuclear science. All you have to do is write down the question, do a basic research about nuclear technology. Basic research in the sense you don't have to dwell deeper into Baba Atomic Research Center or anything. Just go to the BARC website and read about India's nuclear program. It is just a single page. It will run to maximum up to three pages in Microsoft Word. You read it and write an answer based on it, like without any knowledge about it. And then once we complete the portions, try to rewrite the same answer based on the knowledge which you have gained from the classes. This is the overall task. So task 1, before learning. Task 2, after learning. So the second answer, you can send it to me. I'll display the question here. We'll read about these the next class. Yeah, please write the question. So sending you a link in the Zoom. If you search Baba Atomic Research Center, BARC space Anushakti, you will get a page. So basic introduction about India's nuclear program. You can read it once. BARC space Anushakti. Clear. So any other doubts? You can raise your hands. I'll unmute. So since we are winding up like 15 minutes earlier, the last two classes, it may be somewhere close to 2 hours and 45 minutes. I'm telling in advance. Yeah. If you have any doubts, you can drop a message. So plan properly. I'll give you 10 minutes break, but the last two classes will be somewhere close to 2 hours and 45 minutes. Jawar, I have your answer. I remember looking at your answer. I meant to correct it and send reply. Yes, I'll look into it. I'll definitely reply about the IRNSS. I still have it in my mailbox. No problem. I'll reply to you. Yeah. Don't send the present answer to me. Wait for the nuclear science topic to be over and then rewrite it. Good. No other doubts? Can we wind up? Right then. Thank you very much. I'll see you in the next class.